Hello there. It is good to have you with us again. Tonight, we are venturing into the emptiest places in the known universe. Not the space between stars, which still contains roughly 1 atom per cubic centimeter. Not even the space between galaxies, where matter thins to perhaps 1 atom per cubic meter. We are going further, to the cosmic voids, where you could travel for millions of light years and encounter almost nothing at all. These are not simply empty regions. They are the largest structures in existence, some spanning 300 million light years across. And here is what makes them remarkable. The voids are not where matter failed to gather. They are the spaces left behind as gravity pulled everything else away, drawing galaxies into the filaments and walls that now surround these immense bubbles of near nothingness. We will begin here, in our own Milky Way, surrounded by 400 billion stars. Then we will drift outward, past the local group, beyond the Virgo supercluster, until we reach the boundaries where the cosmic web gives way to something else entirely. The Boötes void awaits us, a region so empty that if our galaxy sat at its center, we would not have discovered that other galaxies existed until the 1960s. If these quiet explorations help you find rest, please consider liking and subscribing. It helps others find their way here too. Now, let your breathing slow. The stars outside your window are already beginning to recede. We have a very long way to travel, and the silence ahead is deeper than you can imagine. The universe breathes with light. In this present moment, roughly 13.8 billion years after the initial expansion, the cosmos finds itself in what astronomers call the stelliferous era, the age of stars. It is a time of extraordinary activity, though that activity unfolds across scales so vast that human perception struggles to contain it. Across the observable universe, spanning some 93 billion light-years in diameter, approximately 2 trillion galaxies drift through the expanding fabric of space-time. Within these galaxies, an estimated 200 billion trillion stars burn steadily, converting hydrogen into helium, helium into carbon, carbon into oxygen, and in the most massive cases, forging elements all the way up to iron-56, the most tightly bound nucleus in nature. Consider the Milky Way, the spiral galaxy that serves as humanity's cosmic address. It stretches approximately 100,000 light-years from edge to edge, containing somewhere between 200 and 400 billion stars. At its center lies Sagittarius, a star, a supermassive black hole with a mass of roughly 4 million suns, compressed into a region smaller than the orbit of Mercury. This gravitational anchor holds the galaxy together, though it currently sits in a relatively quiet state, accreting only small amounts of gas and dust from its immediate surroundings. Throughout the Milky Way's spiral arms, new stars continue to form. The process begins in giant molecular clouds, vast reservoirs of cold hydrogen gas, typically between 10 and 15 Kelvin, just a few degrees above absolute zero. These clouds can span hundreds of light years and contain enough mass to form thousands of stars. The Orion Molecular Cloud Complex, located roughly 1,500 light-years from Earth, represents one such stellar nursery. Within it, gravity slowly pulls pockets of gas together, and when the density at the core reaches approximately 10 to the 4th hydrogen molecules per cubic centimeter, collapse accelerates. The journey from diffuse gas to burning star takes roughly 10 million years for a sun-like star. As the protostar contracts, gravitational potential energy converts to heat, raising the core temperature. When that temperature reaches approximately 10 million Kelvin, hydrogen nuclei begin fusing into helium through the proton-proton chain reaction. 4 hydrogen atoms combine to form 1 helium atom, and in the process, 0.7% of their mass converts directly into energy, according to Einstein's mass-energy equivalence. A star is born. The rate of star formation across the Milky Way currently averages between 1 and 3 solar masses per year. This might sound modest, but it represents an enormous amount of activity when considered across cosmic time. In the Orion Nebula alone, approximately 700 young stars have formed within the past few million years, many still surrounded by protoplanetary disks where planets may eventually coalesce. Yet this present rate of star formation represents a significant decline from the universe's peak productivity. Roughly 10 billion years ago, when the cosmos was only 3 to 4 billion years old, galaxies formed stars at rates 10 to 20 times higher than today. The universe was denser then, with more raw material available. Galaxies collided more frequently, their gravitational interactions compressing gas clouds and triggering intense bursts of stellar birth. Some galaxies from that era, called starburst galaxies, produced hundreds of solar masses of new stars every year. The decline happened gradually, like a fire that has consumed much of its fuel. The hydrogen that fills intergalactic space continues to fall into galaxies, but the rate of infall has slowed. Within galaxies themselves, previous generations of stars have processed much of the available hydrogen, locking it away in stellar remnants or expelling it in supernova explosions that sometimes eject material entirely from the galactic disk. The stars that currently populate the universe fall into distinct categories based on their mass, and this mass determines almost everything about their fate. The most massive stars, the blue giants and supergiants, contain 20 to 100 times the mass of the Sun. They burn at surface temperatures exceeding 30,000 Kelvin, appearing brilliant blue-white to any observer. Their luminosity can exceed 1,000,000 times that of the Sun. But this brilliance comes at a cost. They consume their hydrogen fuel with such ferocity that their lifespans measure only in millions of years. A star like Rigel, the blue supergiant in Orion with roughly 21 solar masses, will exhaust its fuel in perhaps 10 million years, a cosmic eye blink. At the opposite extreme lie the red dwarfs, stars with masses between 0.08 and 0.5 times that of the Sun. These dim, cool stars glow at surface temperatures of only 2,500 to 4,000 Kelvin, emitting most of their radiation in infrared wavelengths. Proxima Centauri, the nearest star to the Sun at 4.24 light-years distant, exemplifies this class. With only 12% of the Sun's mass, it burns its fuel so slowly that it will continue shining for trillions of years, far longer than the current age of the universe. Red dwarfs constitute approximately 70% of all stars in the Milky Way. They are everywhere, yet their dimness makes them invisible to the naked eye. Not a single red dwarf can be seen from Earth without a telescope, despite their overwhelming numerical dominance. This fact carries profound implications for the universe's future. The most common stars are also the longest lived, and they will continue burning long after every other stellar type has faded. Between these extremes lie stars like the Sun, classified as G-type main sequence stars or yellow dwarfs. The Sun, with its surface temperature of approximately 5,778 Kelvin and its luminosity of 3.8 times 10 to the 26th watts, represents a middle path. It has burned steadily for 4.6 billion years and will continue for another 5 billion before exhausting its core hydrogen. At that point, it will swell into a red giant, eventually shedding its outer layers to form a planetary nebula, while its core contracts into a white dwarf, a dense stellar remnant about the size of Earth, but containing roughly half the Sun's original mass. White dwarfs represent one possible endpoint of stellar evolution, and they already populate the galaxy in enormous numbers. Approximately 10 billion white dwarfs drift through the Milky Way, the cooling remnants of stars that completed their life cycles over the past several billion years. A newly formed white dwarf begins with a surface temperature exceeding 100,000 Kelvin, glowing blue-white with residual heat. But white dwarfs generate no new energy through fusion. They simply radiate their stored thermal energy into space, cooling gradually over timescales measured in billions of years. The oldest white dwarfs in the galaxy have cooled to temperatures around 4,000 Kelvin, still warm enough to glow dimly, but far cooler than their initial states. Given enough time, far more time than the universe has yet existed, they will cool further, eventually reaching temperatures indistinguishable from the cosmic background. But that process requires timescales on the order of 10 to the 15th power years, a quadrillion years, a number so large it defies intuitive comprehension. Neutron stars represent another category of stellar remnant, formed when stars between roughly 8 and 25 solar masses exhaust their fuel and collapse. The core implosion crushes protons and electrons together, forming neutrons and releasing a burst of neutrinos that carries away most of the gravitational binding energy. What remains is a sphere only 20 kilometers in diameter, but containing 1.4 to 2 solar masses, a density so extreme that a teaspoon of neutron star material would weigh approximately 6 billion tons on Earth. Newly formed neutron stars spin rapidly, some completing hundreds of rotations per second, and they possess magnetic fields trillions of times stronger than Earth's. These fields channel radiation into beams that sweep across space like lighthouse beacons, creating the phenomenon known as pulsars. But over millions of years, neutron stars gradually slow their rotation and their magnetic fields decay, leaving behind cold, dark objects that contribute to the growing population of stellar corpses. The universe, in this present era, remains vibrantly alive. Energy flows from stellar cores outward into space. Galaxies rotate, their stars tracing orbital paths that take hundreds of millions of years to complete. New stars ignite in molecular clouds, while old stars shed their outer layers or collapse into dense remnants. The cosmic web of dark matter and gas stretches between galaxy clusters, channeling material along filaments that span hundreds of millions of light years. But embedded within this activity lies a fundamental truth: the fuel is finite. The hydrogen that powers stellar fusion exists in limited quantities. Every star that forms consumes some portion of this cosmic inheritance, converting it into heavier elements or locking it away in remnants that no longer participate in the cycle of stellar birth and death. The universe has already passed its peak of star formation. The decline, though gradual on human timescales, has begun. The decline reveals itself in the numbers. Across the observable universe, approximately 400 billion galaxies contain the remaining reserves of hydrogen, the primordial fuel that has powered stellar fusion since the first stars ignited some 13.6 billion years ago. Yet this vast reservoir is not inexhaustible. Current estimates suggest that galaxies have already converted roughly 70% of their available hydrogen into stars, stellar remnants, and heavier elements. The cosmic fuel gauge, if such a thing could exist, would show the tank moving steadily toward empty. Consider the Milky Way as a representative case. Our galaxy contains approximately 60 billion solar masses of molecular hydrogen, concentrated primarily in the thin disk, where spiral arms sweep through the interstellar medium. This sounds like an enormous quantity, and by terrestrial standards it is. Enough hydrogen to form perhaps 30 billion stars similar to our Sun. But the consumption rate tells a different story. The Milky Way currently converts between 1 and 3 solar masses of gas into new stars each year. At this pace, the existing molecular hydrogen reserves would be exhausted in roughly 20 to 60 billion years, even without accounting for the gas that escapes the galaxy entirely or becomes locked in forms unavailable for star formation. The situation varies dramatically across different galaxy types. Elliptical galaxies, those massive spheroidal collections of ancient stars, have already depleted most of their hydrogen. Galaxies like Messier 87, the giant elliptical at the heart of the Virgo cluster, contain stellar populations averaging 10 billion years in age. Their star formation rates have dropped to nearly zero, less than 0.01 solar masses per year in many cases. These galaxies represent the future state of all stellar systems, collections of aging stars slowly burning through their remaining fuel with no new generations to replace them. Spiral galaxies like the Milky Way and Andromeda maintain higher star formation rates because their rotating disk structures allow gas to concentrate in spiral arms, where gravitational compression triggers collapse. The density waves that create these spiral patterns sweep through the disk at speeds of roughly 200 kilometers per second relative to the orbiting gas, compressing molecular clouds and initiating the formation of new stellar nurseries. But even this mechanism operates on borrowed time. The gas supply diminishes with each stellar generation, and the efficiency of star formation, the fraction of available gas that actually collapses into stars, remains stubbornly low, typically between 1 and 10% per freefall time of a molecular cloud. Irregular galaxies and dwarf systems present yet another variation, the Large Magellanic Cloud, orbiting the Milky Way at a distance of roughly 160,000 light-years, contains proportionally more gas than our galaxy relative to its stellar mass. Its star formation rate of approximately 0.2 solar masses per year might seem modest, but scaled to its size, this represents vigorous stellar production. The Tarantula Nebula within the Large Magellanic Cloud ranks among the most active star-forming regions in the local group, containing stars with masses exceeding 100 times that of the Sun. These massive stars burn through their hydrogen in mere millions of years, a cosmic eye blink, before exploding as supernovae and enriching the surrounding gas with heavy elements. The enrichment process itself affects future star formation in subtle ways. As successive stellar generations live and die, they seed the interstellar medium with elements heavier than hydrogen and helium, what astronomers collectively call metals. The Sun, a relatively young star at 4.6 billion years old, contains roughly 2% metals by mass, inherited from the gas cloud that collapsed to form it. This metallicity influences how efficiently gas can cool and collapse. Higher metallicity gas radiates energy more effectively, allowing clouds to fragment into smaller pieces and potentially forming more low-mass stars. But it also means that each new stellar generation locks away more of the original hydrogen in forms that cannot easily return to the star-forming cycle. The recycling of stellar material operates on vastly different timescales, depending on stellar mass. A star like the Sun will eventually shed its outer layers as a planetary nebula, returning perhaps 40% of its original mass to the interstellar medium. But this process takes roughly 10 billion years from birth to completion. More massive stars recycle material faster. A 20 solar mass star might live only 10 million years before exploding, but they are far rarer. For every star above 8 solar masses that will end in a supernova, there are hundreds of lower mass stars that will take billions of years to return their gas. The lowest mass stars return almost nothing at all. Red dwarfs, those dim stellar embers with masses below 0.4 solar masses, are fully convective. They mix their entire hydrogen supply throughout their interiors, burning fuel with extraordinary efficiency. A red dwarf of 0.1 solar masses will shine for approximately 10 trillion years, nearly 1,000 times the current age of the universe, before exhausting its hydrogen. When it finally does, it will contract directly into a helium-white dwarf without shedding significant mass. The hydrogen locked within these stars is effectively removed from the cosmic fuel supply for timescales that dwarf all of recorded cosmic history. Red dwarfs dominate the stellar population by number. Roughly 75% of all stars in the Milky Way belong to this category, and their prevalence only increases as time passes. Each generation of star formation produces more low-mass stars than high-mass ones, following a distribution called the initial mass function. For every star born with 10 solar masses, approximately 200 stars form with masses below 0.5 solar masses. This statistical reality means that the universe is gradually locking its hydrogen into the longest-lived, least luminous stellar containers. A slow but inexorable transfer of fuel from the active cycle to permanent storage. The intergalactic medium offers no salvation. While vast quantities of hydrogen exist in the cosmic web, the filamentary structure of gas and dark matter connecting galaxy clusters, most of this material is too hot and diffuse to collapse into stars. The intergalactic medium maintains temperatures of 100,000 to 10 million Kelvin, heated by gravitational compression and the ultraviolet radiation from quasars and young galaxies. At these temperatures, hydrogen exists as ionized plasma, its atoms stripped of electrons and unable to form the molecular hydrogen necessary for star formation. Some of this hot gas does cool and fall into galaxies over billions of years, providing fresh fuel, but the rate of this cosmic accretion is declining as the universe expands and the average density of the intergalactic medium decreases. The expansion itself plays a crucial role. As space stretches, the density of matter in the universe drops. Galaxies that might have merged and combined their gas reserves are instead carried apart by the accelerating expansion driven by dark energy. The Milky Way and Andromeda will collide in approximately 4.5 billion years, combining their remaining hydrogen into a single larger galaxy. But most galaxies in the observable universe are already receding from each other too quickly for gravity to overcome. The fuel that exists within each galaxy represents, increasingly, all the fuel that galaxy will ever have. The most luminous stars will be the first to vanish from this cosmic stage. While red dwarfs measure their existence in trillions of years, and sun-like stars burn steadily for 10 billion, the blue giants, those stellar titans with masses exceeding 8 times that of the Sun, consume their nuclear fuel with a profligacy that seals their fate within mere millions of years. Consider a star of 20 solar masses, burning with a surface temperature of 30,000 Kelvin, its blue-white luminosity outshining the Sun by a factor of 100,000. This brilliance comes at a cost measured in hydrogen consumption rates that dwarf smaller stars by orders of magnitude. The core of such a giant fuses approximately 600 million metric tons of hydrogen into helium every second, a rate so extreme that its main sequence lifetime spans only 8 million years. In cosmic terms, these stars are mayflies, brilliant and brief, their entire existence fitting within the span of time it takes the Sun to complete a single orbit around the galactic center. The physics governing this brevity follows directly from the relationship between mass and luminosity. A star's energy output scales roughly as the cube of its mass, while its fuel supply scales only linearly. Double a star's mass, and it burns through its reserves 8 times faster. The most massive stars known, hypergiants exceeding 100 solar masses, may exhaust their core hydrogen in as little as 2 million years, their cores reaching temperatures of 40 million Kelvin as they race through their nuclear evolution. When the hydrogen in a massive star's core is finally depleted, the star does not simply fade. Instead, it begins a complex sequence of nuclear burning stages, each shorter and more desperate than the last. The helium ash accumulated from hydrogen fusion now becomes fuel itself, igniting at a core temperature of approximately 100 million Kelvin. Helium nuclei, alpha particles, fuse in a process called the triple alpha reaction, combining to form carbon-12 and releasing energy that temporarily stabilizes the core against gravitational collapse. This helium-burning phase lasts perhaps 1 million years in a 20 solar mass star. When the helium is exhausted, the carbon core contracts and heats until carbon fusion ignites at 600 million Kelvin. Carbon burning produces neon, sodium, and magnesium, and lasts only about 1,000 years. The pace accelerates with each successive stage. Neon burning at 1.2 billion Kelvin consumes the core in approximately 1 year. Oxygen burning at 1.5 billion Kelvin lasts mere months. Finally, silicon burning at 2.7 billion Kelvin, the last exothermic fusion process available, completes in roughly 1 day. Each of these burning stages produces heavier elements, and the star develops an onion-like structure, concentric shells of different compositions, each burning a different fuel, surrounding an ever denser core. The outermost layers still fuse hydrogen. Beneath them, helium burns to carbon. Deeper still, carbon fuses to neon, neon to oxygen, oxygen to silicon. At the very center, silicon fuses to produce iron-56 and its neighboring isotopes, the end of the line for stellar nucleosynthesis. Iron-56 represents a fundamental boundary in nuclear physics. Its nucleus possesses the highest binding energy per nucleon of any element, meaning that neither fusing iron into heavier elements nor splitting it into lighter ones releases energy. Both processes require energy input. When a massive star's core becomes dominated by iron, it has built a time bomb at its center. No further fusion can provide the pressure support needed to counteract gravity. The core, now roughly 1.5 solar masses compressed into a sphere the size of Earth, is supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed into the same quantum states. The collapse, when it comes, unfolds with terrifying speed. As the iron core grows beyond the Chandrasekhar limit of approximately 1.4 solar masses, electron degeneracy pressure fails. Electrons are forced to combine with protons through inverse beta decay, producing neutrons and neutrinos. The core collapses at velocities approaching 1/4 the speed of light, compressing from Earth-sized to a sphere roughly 20 kilometers in diameter in less than 1 second. The density reaches 400 trillion grams per cubic centimeter, the density of an atomic nucleus. The collapse halts abruptly when the core reaches nuclear density, and neutron degeneracy pressure provides a new, far more rigid resistance. The infalling outer layers of the star, still plummeting inward at 70,000 kilometers per second, slam into this suddenly rigid core and rebound. A shockwave propagates outward, energized by the flood of neutrinos escaping the neutronized core. These neutrinos carry away 99% of the gravitational binding energy released in the collapse, approximately 3 × 10⁻46 power joules, while the remaining 1% powers the visible explosion. This is a core collapse supernova, one of the most energetic events in the universe. For a few weeks, a single dying star can outshine its entire host galaxy, radiating 10 billion times the sun's luminosity. The explosion ejects the star's outer layers at velocities of 10,000 to 30,000 kilometers per second, enriching the interstellar medium with heavy elements forged in the star's core and in the explosion itself. Elements heavier than iron, gold, platinum, uranium, are synthesized in the intense neutron flux of the supernova through rapid neutron capture, the R process. The Milky Way currently hosts approximately 1 core collapse supernova every 50 years on average. Each one marks the death of a star that formed only millions of years earlier, a star that burned so brightly it could not sustain itself. The remnants of these explosions, expanding shells of enriched gas, and at their centers, neutron stars or black holes, accumulate throughout the galaxy. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova observed by Chinese astronomers in 1054 CE. At its heart spins a neutron star 20 kilometers across, rotating 30 times per second, its magnetic field 1 trillion times stronger than Earth's. As the universe ages and star formation declines, the population of massive stars will dwindle. These stars form from the densest regions of molecular clouds, requiring substantial reservoirs of cold gas to achieve their great masses. As the hydrogen supply diminishes, fewer clouds will reach the critical density needed to birth blue giants. The supernovae will become rarer, their light punctuating the cosmic darkness with decreasing frequency. Within the next few trillion years, the last massive stars will complete their brief, violent lives. The final core collapse supernovae will detonate in galaxies grown dim and quiet, their light traveling across an ever emptier universe. The heavy elements they scatter will have fewer opportunities to be incorporated into new stars, as star formation itself winds down toward cessation. The universe will remember these giants only through their remnants, the neutron stars slowly cooling, the black holes slowly growing, and the enriched gas that will never again coalesce into new suns. As the blue giants exhaust themselves and the supernovae grow silent, a different class of star will inherit the cosmos. These are the red dwarfs, the smallest, coolest, and most patient stellar furnaces in existence. Where massive stars burn through their fuel in mere millions of years, red dwarfs will persist for timescales that dwarf the current age of the universe by factors of hundreds or even thousands. A red dwarf is defined by its mass, between roughly 0.08 and 0.45 solar masses. Below 0.08 solar masses, an object lacks sufficient gravitational pressure to sustain hydrogen fusion in its core, becoming instead a brown dwarf, a failed star that merely glows with the residual heat of its formation. Above 0.45 solar masses, stars begin to develop the internal structure that leads to faster burning and shorter lives. But within this narrow mass range exists a stellar design of remarkable efficiency. The physics of red dwarf longevity begins with temperature. The core of a red dwarf reaches temperatures between 3 and 10 million Kelvin, hot enough to fuse hydrogen into helium through the proton-proton chain, but far cooler than the 15 million Kelvin found in the Sun's core. This lower temperature means the fusion reactions proceed more slowly. The rate of nuclear fusion depends extraordinarily sensitively on temperature, roughly proportional to the fourth power of temperature for the proton-proton chain. A core that is half as hot produces fusion energy at roughly 1/16 the rate. This reduced energy output means the star consumes its hydrogen fuel with extreme parsimony. But temperature alone does not explain the trillion-year lifespans. The second factor is convection. In the Sun, energy generated in the core must travel outward through a radiative zone where photons bounce randomly between atoms, taking perhaps 170,000 years to reach the convective outer layer. The core remains isolated from the outer envelope, burning through its central hydrogen while the outer layers remain largely untouched. When the Sun exhausts its core hydrogen in approximately 5 billion years, it will still possess substantial hydrogen in its outer regions. fuel that the core can never access. Red dwarfs below about 0.35 solar masses operate differently. These fully convective stars mix their entire volume continuously, like a pot of water at a rolling boil. Hydrogen from the outer layers circulates down to the core, while helium produced by fusion rises and disperses throughout the star. This constant mixing means the red dwarf can access its entire hydrogen supply, not merely the fraction trapped in its core. A red dwarf of 0.1 solar masses contains roughly 10% of the Sun's hydrogen, but it can burn nearly all of it rather than the roughly 10% the Sun will consume before leaving the main sequence. Consider Proxima Centauri, the closest star to the Sun at 4.24 light-years distance. This red dwarf possesses approximately 0.12 solar masses and a surface temperature of about 3042 Kelvin, cool enough that it glows a deep crimson rather than the yellow-white of the Sun. Its luminosity measures only 0.0017 times solar luminosity, meaning it produces less than 0.2% of the Sun's light. At this miserly rate of energy production, Proxima Centauri will remain on the main sequence for approximately 4 trillion years, nearly 300 times longer than the Sun's main sequence lifetime, and almost 300 times longer than the current age of the universe. The smallest red dwarfs achieve even more extreme longevity. A star of 0.08 solar masses, barely massive enough to sustain fusion, burns so slowly that theoretical models predict main sequence lifetimes exceeding 10 trillion years. These stars produce only about 0.01% of the Sun's luminosity, their surfaces barely reaching 2300 Kelvin. They glow with a light so red it borders on infrared, nearly invisible to human eyes. Yet they will still be fusing hydrogen when the universe is 1,000 times its current age. The abundance of red dwarfs makes their longevity cosmically significant. Approximately 75% of all stars in the Milky Way are red dwarfs. Within 10 parsecs of the Sun, a sphere containing roughly 350 known stellar systems, red dwarfs account for about 250 of them. The galaxy contains an estimated 200 to 300 billion red dwarfs, each one a potential trillion-year beacon. When all other stars have died, these dim furnaces will constitute the remaining stellar population. As red dwarfs age, they undergo a gradual transformation, unlike anything seen in more massive stars. Because they are fully convective, they do not develop the helium cores that cause sun-like stars to expand into red giants. Instead, they slowly convert their entire hydrogen supply into helium, growing slightly hotter and bluer as their mean molecular weight increases. A red dwarf that begins its life at 3000 Kelvin will warm to perhaps 3,500 or 4,000 Kelvin over trillions of years, its color shifting from deep red toward orange. Near the end of their lives, red dwarfs will briefly become blue dwarfs, a theoretical stellar class that has never been observed because the universe is far too young for any red dwarf to have reached this stage. These blue dwarfs will shine with several times their original luminosity as they burn through their final hydrogen reserves, their surfaces reaching temperatures of 6,000 to 7,000 Kelvin. For a few billion years, they will resemble small, hot versions of the Sun before finally exhausting their fuel and contracting into helium-white dwarfs. The transition from red dwarf to white dwarf will proceed without the dramatic planetary nebula phase that accompanies the death of sun-like stars. Red dwarfs lack the mass to drive powerful stellar winds that strip away outer layers. Instead, they will simply fade, their fusion reactions sputtering to a halt as the last hydrogen nuclei find each other and combine. The resulting white dwarfs will be small, perhaps 0.1 to 0.4 solar masses, and composed almost entirely of helium, lacking the carbon-oxygen cores of white dwarfs descended from more massive stars. In the far future, trillions of years hence, the universe will enter a period when red dwarfs dominate the stellar census not merely by number, but by being the only stars remaining. The blue giants will be ancient history, their supernovae having detonated billions of times over. Sun-like stars will have completed their red giant phases and settled into white dwarf retirement. Only the red dwarfs will persist, scattered through galaxies grown dark and quiet, their feeble light the only stellar illumination in an aging cosmos. These patient stars will witness the gradual transformation of their galactic homes. They will orbit through merging galaxies, survive close encounters with stellar remnants, and occasionally be ejected into intergalactic space by gravitational interactions. Some will acquire planets from disrupted systems, while others will lose their own worlds to passing stars. Through it all, they will continue their slow fusion, converting hydrogen to helium one proton-proton reaction at a time. The energy released by a single proton-proton chain reaction amounts to 26.7 million electron volts, a quantity that seems substantial until one considers that a red dwarf must perform this reaction approximately 10 to the 38th power times per second to maintain even its meager luminosity. Yet even at this rate, the fuel supply of a small red dwarf will last for cosmic ages. The star simply waits, burning steadily, as the universe around it grows older and emptier. While the red dwarfs continue their patient vigil, another class of stellar remnant embarks on a journey measured not in fusion reactions, but in the slow surrender of stored heat. The white dwarfs, the exposed cores of stars that have exhausted their nuclear fuel, begin their descent toward absolute darkness, a cooling process that will span timescales far exceeding the current age of the universe. A white dwarf forms when a star between roughly 0.5 and 8 solar masses reaches the end of its hydrogen and helium burning phases. The outer layers drift away as a planetary nebula, leaving behind a dense core composed primarily of carbon and oxygen nuclei, with traces of heavier elements depending on the progenitor star's mass. This remnant typically contains between 0.5 and 1.4 solar masses compressed into a sphere roughly the size of Earth, approximately 12,000 kilometers in diameter. The resulting density reaches extraordinary values. 1 cubic centimeter of white dwarf material weighs approximately 1 metric ton, or about 1 million times the density of water. The physics that prevents further collapse belongs to the quantum realm. Electrons, being fermions, obey the Pauli exclusion principle. No two electrons can occupy the same quantum state simultaneously. When matter is compressed to white dwarf densities, the electrons are forced into increasingly high-energy quantum states, creating a pressure that resists gravitational collapse. This electron degeneracy pressure depends not on temperature, but on density alone, which explains why a white dwarf can cool indefinitely without shrinking further. The star has reached a stable configuration that will persist for eons. At the moment of formation, a white dwarf blazes with surface temperatures exceeding 100,000 Kelvin, far hotter than the surface of the Sun, which registers approximately 5,800 Kelvin. This intense heat represents the thermal energy accumulated during billions of years of nuclear fusion, now trapped within a crystalline lattice of carbon and oxygen ions. The white dwarf possesses no internal energy source. It can only radiate away what it already contains. The cooling process begins immediately. The rate of cooling follows well-understood thermodynamic principles. A white dwarf radiates energy according to the Stefan Boltzmann law, with luminosity proportional to the fourth power of surface temperature. Initially, when temperatures remain high, the cooling proceeds rapidly. A white dwarf at 100,000 Kelvin might cool to 20,000 Kelvin within its first 100 million years. But as the temperature drops, the rate of energy loss decreases dramatically. Cooling from 10,000 Kelvin to 5,000 Kelvin requires billions of years. Cooling from 5,000 Kelvin to 4,000 Kelvin requires tens of billions more. The oldest white dwarfs currently observable in the Milky Way have been cooling for approximately 11 to 12 billion years. These ancient stellar corpses, found in globular clusters and the galactic halo, display surface temperatures around 3,500 to 4,000 Kelvin, cool enough to glow with a dim reddish light, fainter than the feeblest red dwarf. Their luminosities have dropped to roughly 1/10,000th of the Sun's output. Yet even these venerable remnants remain far from their ultimate fate. As cooling continues over billions of years, a remarkable phase transition occurs within the white dwarf's interior. The carbon and oxygen ions, initially behaving as a hot plasma, gradually lose thermal energy until their electrostatic repulsion can no longer overcome the organizing influence of their mutual interactions. The ions settle into a regular crystalline lattice. The white dwarf literally freezes from the center outward. This crystallization releases latent heat, temporarily slowing the cooling process, much as water releases heat when it freezes into ice. Observations from the Gaia spacecraft have confirmed this crystallization process. By measuring the luminosities and colors of thousands of white dwarfs, astronomers detected a pile-up of objects at specific luminosities, a signature of the temporary heating that crystallization provides. The data suggests that a typical 0.6 solar mass white dwarf begins crystallizing when its core temperature drops to approximately 6 million Kelvin, and the process continues for roughly 1 to 2 billion years as the crystallization front propagates outward. The crystalline structure that forms resembles a body-centered cubic lattice, with carbon and oxygen ions arranged in a repeating geometric pattern. In some white dwarfs, gravitational settling causes the heavier oxygen nuclei to sink toward the center, while lighter carbon nuclei float upward, a process called chemical differentiation that releases additional gravitational energy and further delays cooling. The interior of an old white dwarf thus becomes stratified, an oxygen-rich crystalline core surrounded by a carbon-rich crystalline mantle, all enclosed by a thin envelope of hydrogen and helium. As eons pass and temperatures continue to drop, the white dwarf's luminosity fades toward invisibility. After approximately 10 to the 15th years, 1 quadrillion years, or roughly 100,000 times the current age of the universe, a typical white dwarf will have cooled to temperatures approaching the cosmic microwave background radiation, currently 2.7 Kelvin, but itself cooling as the universe expands. At this point, the white dwarf can no longer radiate energy faster than it absorbs it from the ambient radiation field. The cooling effectively stalls. This final state represents the theoretical endpoint called a black dwarf, a white dwarf that has cooled so completely that it emits no significant radiation. The object persists as a dark, crystalline sphere of degenerate matter, invisible against the blackness of space. No black dwarfs yet exist in our universe. The cosmos is simply too young. The oldest white dwarfs have completed barely 1% of their journey toward this ultimate darkness. The mass of a white dwarf determines certain aspects of its fate. More massive white dwarfs, approaching the Chandrasekhar limit of approximately 1.4 solar masses, possess smaller radii due to the stronger gravitational compression. A 1.3 solar mass white dwarf might measure only 4,000 kilometers in diameter, smaller than Mars. These compact remnants cool more slowly in some respects because their smaller surface area reduces the rate of energy radiation, yet their higher internal densities also affect heat transport in complex ways. The thermal conductivity within a white dwarf depends on the degenerate electrons, which carry heat efficiently through the crystalline lattice. As the star cools and the crystal structure becomes more ordered, the conductivity actually increases. The electrons scatter less frequently from the increasingly regular ion lattice. This means that old, cold white dwarfs maintain nearly uniform internal temperatures, with heat flowing readily from core to surface. In the far future, after the last red dwarfs have exhausted their hydrogen and themselves become white dwarfs, the universe will contain an enormous population of these cooling remnants. Current estimates suggest the Milky Way alone harbors approximately 10 billion white dwarfs, and this number will grow substantially as sun-like stars complete their evolution. Each of these objects will follow its own cooling curve, gradually dimming over quadrillions of years. The transition from white dwarf to black dwarf represents not a dramatic event, but an asymptotic approach. There is no sharp boundary, no moment of final darkness, only an endless diminishment. The surface temperature drops from thousands of Kelvin to hundreds, from hundreds to tens, from tens toward the irreducible minimum set by the cooling cosmic background. The luminosity fades from a 10,000th of the sun to a millionth, from a millionth to a billionth, ever downward toward values too small to measure. Throughout this immense span of time, the black dwarf remains structurally stable. Electron degeneracy pressure continues to support the star against gravity. The crystalline lattice holds its form. The carbon and oxygen nuclei remain locked in their geometric arrangement, patient and unchanging. Only the thermal energy departs, photon by photon, into the expanding void. Beyond the crystalline remnants of ordinary stars, Another class of stellar corpse traces its own path toward thermal oblivion. The neutron stars, those impossibly dense spheres born in the violent collapse of massive stellar cores, carry within them conditions found nowhere else in the natural universe. Where white dwarfs compress matter to densities of 1,000,000 grams per cubic centimeter, neutron stars achieve densities 100 million times greater still. A single teaspoon of neutron star material would weigh approximately 6 billion tons on Earth's surface, more than the combined mass of every human being who has ever lived. These objects form in the final moments of core collapse supernovae, when the iron core of a massive star can no longer sustain itself against gravitational pressure. The collapse happens in milliseconds. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos that carry away the binding energy of the newly formed compact object. What remains is a sphere roughly 20 kilometers in diameter, smaller than many cities, yet containing between 1.4 and 2.1 solar masses of material. The surface gravity reaches values 200 billion times stronger than Earth's, and the escape velocity approaches 2/3 the speed of light. At birth, neutron stars emerge from their supernova cocoons with temperatures exceeding 100 billion Kelvin in their cores, hotter than the center of any ordinary star. Their surfaces, though cooler, still radiate at temperatures of several million Kelvin, glowing fiercely in X-rays. But this thermal energy represents only one aspect of their remarkable initial endowment. Newly formed neutron stars also possess magnetic fields of staggering intensity, typically ranging from 100 million to 1 trillion times stronger than Earth's magnetic field. The most extreme examples, called magnetars, generate fields reaching 1 quadrillion Gauss, strong enough to distort the electron orbitals of atoms at distances of thousands of kilometers, strong enough to make the vacuum of space itself become birefringent. These magnetic fields arise from the conservation of magnetic flux during the collapse. The original stellar core, perhaps 200,000 kilometers across, possessed a modest magnetic field. When that core compressed to a sphere 20 kilometers in diameter, the field lines concentrated by a factor of 100 million. The result is a magnetic dynamo of extraordinary power, capable of accelerating particles to relativistic velocities and generating beams of radio waves, X-rays, and gamma rays that sweep across the cosmos like lighthouse beacons. The decay of these magnetic fields proceeds through multiple physical mechanisms operating on vastly different timescales. In the outer crust of the neutron star, where matter exists as a lattice of neutron-rich nuclei immersed in a sea of degenerate electrons, the magnetic field dissipates through ohmic decay, the same process that causes electrical currents to fade in ordinary conductors, though operating under conditions of extreme density and temperature. The electrical resistivity of neutron star crust material depends sensitively on temperature, impurity content, and the precise composition of the nuclear lattice. At temperatures of 100 million Kelvin, the ohmic decay timescale measures in millions of years. As the star cools, the resistivity drops and the decay slows, stretching the timescale to billions and eventually trillions of years. Deeper within the neutron star, in the inner crust and core, where matter transitions from crystalline nuclei to a continuous fluid of neutrons with a small admixture of protons and electrons, different physics governs the magnetic evolution. Here, the neutrons form a superfluid, a quantum state of matter in which particles flow without viscosity, while the protons form a superconductor, carrying electrical currents without resistance. In this regime, magnetic flux becomes quantized into discrete bundles called fluxoids, each carrying exactly one quantum of magnetic flux. The magnetic field cannot simply diffuse through the superconducting material. Instead, it must evolve through the motion of these quantized flux tubes. The interaction between the neutron superfluid and the proton superconductor creates complex dynamics that researchers continue to study through theoretical models and observations of pulsar behavior. Flux tubes can become pinned to the crystal lattice of the inner crust, creating a reservoir of magnetic energy that releases sporadically through sudden unpinning events. These events may explain the glitches observed in pulsar timing, sudden small increases in rotation rate that occur when angular momentum transfers from the faster spinning superfluid interior to the slower spinning crust. Over timescales of 10 million to 100 million years, the magnetic fields of ordinary neutron stars decay from their initial values of 10 to the 12th Gauss down to 10 to the 8th or 10 to the 9th Gauss. The pulsars that once swept their radio beams across interstellar space grow dim and eventually fall silent as their magnetic dynamos weaken below the threshold needed to generate coherent emission. The pulsar death line, a boundary in the space of magnetic field strength versus rotation period, marks where this transition occurs. Below this line, the electric fields induced by the rotating magnetic dipole can no longer accelerate particles to the energies required for pair production and radio emission. The thermal evolution of neutron stars proceeds in parallel with their magnetic decay, governed by a different set of physical processes. In the first few seconds after formation, neutrino emission dominates the cooling. The core temperature of 100 billion Kelvin drives rapid neutrino production through processes involving the weak nuclear force. The modified Urca process in standard neutron star matter, or the more efficient direct Urca process if the proton fraction exceeds a critical threshold of approximately 100 billion Kelvin 11%. These neutrinos escape directly from the stellar interior, carrying away energy at rates that would drain the thermal content of an ordinary star in microseconds. Within the first million years, neutrino cooling reduces the core temperature to roughly 100 million Kelvin. The surface temperature, regulated by the thermal conductivity of the crust, drops to approximately 1 million Kelvin, and the star's luminosity falls to perhaps 1% of the sun's output, radiated primarily in soft X-rays. This is the epoch when neutron stars remain detectable to X-ray telescopes, their thermal emission revealing the exotic physics of their interiors through subtle features in their spectra and cooling curves. After approximately 1 million years, photon emission from the surface begins to dominate over neutrino emission from the core. The cooling rate slows as the star enters a photon cooling era that extends for billions of years. The surface temperature continues to decline from 1 million Kelvin to 100,000, from 100,000 to 10,000. and the peak of the thermal emission shifts from X-rays to ultraviolet to visible light to infrared. A neutron star 1 billion years old might possess a surface temperature of 30,000 Kelvin, still warm by terrestrial standards, but representing an enormous decline from its incandescent birth. The crystallization of the neutron star crust affects the cooling trajectory in subtle ways. As the temperature drops, the ions in the outer crust freeze into a body-centered cubic lattice, releasing latent heat that temporarily slows the cooling. The inner crust, with its exotic nuclear species and neutron drip, crystallizes at lower temperatures, providing additional thermal reservoirs. The specific heat of the stellar material, dominated by the degenerate electrons in the crust and the neutrons in the core, determines how much the temperature drops for each unit of energy radiated away. On timescales of 10 trillion years and beyond, neutron stars approach the same thermal fate as white dwarfs, an asymptotic cooling toward the temperature as the cosmic microwave background, which itself continues to redshift and diminish as the universe expands. The surface temperature drops below 1000 Kelvin, below 100 Kelvin, below 10 Kelvin, approaching values indistinguishable from the ambient radiation field. The magnetic fields, having decayed through billions of years of ohmic dissipation and flux tube dynamics, weaken to values comparable to interstellar magnetic fields, perhaps 1/1,000,000th of a Gauss, 1,000,000,000,000 times weaker than their birth endowment. What remains is a cold, dark sphere of degenerate matter, its neutrons locked in their quantum mechanical ground state, its protons and electrons in equilibrium, its magnetic field a faint echo of former glory. The neutron star has become a black dwarf of a different composition, not carbon and oxygen supported by electron degeneracy, but neutrons supported by neutron degeneracy pressure and the strong nuclear force. It drifts through the expanding void, gravitationally bound but thermally inert, awaiting the far deeper timescales when even the stability of matter itself comes into question. The cold neutron stars drift through a cosmos that is itself growing quieter, its stellar nurseries slowly closing their doors. For while the remnants of past generations cool toward thermal equilibrium, the raw material for future generations, the vast molecular clouds that once birthed stars by the millions, approaches exhaustion. These stellar nurseries are not infinite reservoirs. The giant molecular clouds that populate spiral galaxies like the Milky Way represent the densest concentrations of matter in the interstellar medium, yet their total mass constitutes only a small fraction of galactic matter. A typical giant molecular cloud spans perhaps 100 to 300 light-years across and contains between 10,000 and 2 million solar masses of material, predominantly molecular hydrogen, at temperatures hovering near 10 to 20 Kelvin. Cold enough that hydrogen atoms pair into H2 molecules and the thermal motion of particles slows to a crawl. The Milky Way currently hosts approximately 6,000 such clouds, with a combined mass of roughly 1 to 2 billion solar masses of molecular gas. This sounds substantial until one considers the consumption rate. Star formation across the galaxy converts approximately 1 to 3 solar masses of gas into stars each year. At this rate, the existing molecular cloud inventory would be depleted in roughly 1 billion years. a mere cosmic moment compared to the trillion-year lifespans of red dwarfs. But the calculation is more complex than simple division. Molecular clouds are not static reservoirs waiting to be drained. They form, evolve, and dissipate on timescales of 10 to 30 million years, assembled from the diffuse atomic hydrogen of the galactic disk through gravitational instabilities, spiral arm compression, and turbulent flows. The atomic hydrogen reservoir is larger, perhaps 5 billion solar masses in the Milky Way, but it too is finite, and the processes that convert atomic gas to molecular gas and then to stars operate within a closed system that receives diminishing inputs from intergalactic space. The physics of molecular cloud formation reveals why this process cannot continue indefinitely. Atomic hydrogen in the galactic disk exists at temperatures near 8,000 Kelvin, too warm and too diffuse to collapse under its own gravity. For stars to form, this gas must first cool and condense. Cooling occurs through radiation. Atoms and molecules emit photons that carry energy away into space. The most efficient coolants are trace elements heavier than hydrogen and helium, carbon, oxygen, and their molecular combinations like carbon monoxide. These species, forged in previous generations of stars and dispersed by stellar winds and supernovae, enable the gas to shed thermal energy and contract. As gas cools below approximately 100 Kelvin, hydrogen atoms begin to combine on the surfaces of microscopic dust grains, silicate and carbonate particles typically measuring 1 micrometer across. These grains act as catalysts, providing surfaces where hydrogen atoms can meet and bond into H2 molecules. The molecular hydrogen that results cannot cool efficiently on its own at low temperatures, but carbon monoxide, present at roughly 1 CO molecule per 10,000 H2 molecules, radiates effectively at the 10 to 20 Kelvin temperatures of molecular cloud interiors. The gene's mass determines whether a given region of molecular cloud will collapse to form stars. This critical mass depends on temperature and density. Lower temperatures and higher densities reduce the gene's mass, allowing smaller fragments to undergo gravitational collapse. In typical molecular cloud cores, the gene's mass falls to roughly 1 solar mass, explaining why sun-like stars and smaller red dwarfs dominate stellar populations. The densest cores, where number densities reach 10,000 to 1 million molecules per cubic centimeter, spawn the protostars that will eventually ignite nuclear fusion. Yet each generation of star formation depletes the available gas, while simultaneously disrupting the very clouds that birthed it. Massive stars, though rare, exert disproportionate influence on their surroundings. A single O-type star with 50 solar masses produces ultraviolet radiation intense enough to ionize hydrogen within a sphere tens of light years across, creating an HII region where temperatures soar to 10,000 Kelvin and molecular bonds shatter. The radiation pressure and stellar winds from such stars can disperse an entire molecular cloud within 3 to 5 million years, far shorter than the cloud's natural lifetime. When massive stars exhaust their fuel and explode as supernovae, the blast waves propagate outward at thousands of kilometers per second, sweeping up and compressing interstellar gas. This compression can trigger new star formation in adjacent clouds, but it also injects turbulent energy that supports clouds against collapse and heats the surrounding medium. The net effect is complex. Supernovae both stimulate and suppress star formation, but over cosmic timescales, the energy injection gradually reduces the efficiency of gas-to-star conversion. The star formation efficiency of molecular clouds, the fraction of cloud mass that actually becomes stars before the cloud disperses, is remarkably low. Observations indicate that only 1 to 10% of a molecular cloud's mass ends up in stars. The remainder is returned to the diffuse interstellar medium, heated and dispersed by the very stars the cloud produced. This inefficiency extends the timeline of star formation, but does not prevent eventual exhaustion. Galactic fountains and chimneys further complicate the gas budget. Supernova explosions in the galactic disk can propel hot gas thousands of light years above the plane, creating bubbles and chimneys that vent material into the galactic halo. Some of this gas eventually cools and falls back to the disk, recycling into future molecular clouds. But some escapes entirely, lost to intergalactic space at velocities exceeding the galaxy's escape speed of roughly 500 kilometers per second. The Milky Way does receive some fresh gas from external sources. High-velocity clouds, clumps of neutral hydrogen falling toward the galactic disk from the halo, deliver perhaps 0.1 to 0.5 solar masses per year. The Magellanic Stream, a ribbon of gas torn from the large and small Magellanic clouds by tidal forces, may contribute additional material over billions of years. But these inputs cannot match the consumption rate. The galaxy is slowly exhausting its star-forming potential. Other galaxies face similar fates at different rates. Elliptical galaxies, having consumed or expelled most of their gas in ancient starbursts, already exist in a post-star forming state. Their stellar populations age without replacement, dominated by red giants and cooling white dwarfs. Spiral galaxies like the Milky Way retain more gas, but are steadily depleting it. Dwarf irregular galaxies, with their shallow gravitational wells, lose gas easily to stellar feedback, and may exhaust their reserves within a few billion years. The cosmic star formation rate peaked approximately 10 billion years ago, when the universe was roughly 3.8 billion years old. At that epoch, galaxies converted gas to stars at rates 5 to 10 times higher than today. The decline since then reflects the gradual exhaustion of the primordial hydrogen that condensed into galaxies during the first billion years. No new hydrogen is being created. The Big Bang produced all the hydrogen that will ever exist, and nuclear fusion in stars only destroys it, converting it to helium and heavier elements. By the time the universe reaches 100 billion years of age, roughly 7 times its current span, the star formation rate will have declined by orders of magnitude. The giant molecular clouds will have largely dissipated, their material locked in stellar remnants or dispersed too thinly to collapse. The spiral arms that currently organize star formation will have wound up and dissolved as galactic dynamics evolve. The last pockets of molecular gas will persist in the densest regions, shielded from disruption, but even these will eventually succumb to the patient erosion of cosmic rays, ultraviolet background radiation, and the slow gravitational stirring of passing stellar remnants. The final stars to form will emerge from these last molecular refuges, predominantly red dwarfs, since the gene's mass in cold, low metallicity gas favors low-mass objects. These ultimate stellar generations will ignite their hydrogen fusion with the same physics that powered the first stars, but in a universe grown dark and sparse. Their birth cries will echo through emptier space, their light traveling farther before encountering another luminous object. Yet even as these final red dwarfs flicker into existence from the last molecular refuges, a far more numerous population of objects will form alongside them. Bodies that approach the threshold of stellar ignition but never quite cross it. These are the brown dwarfs, the failed stars, objects that accumulate enough mass to glow with the heat of gravitational contraction, but never achieve the sustained hydrogen fusion that defines true stellar existence. They represent a boundary condition in astrophysics, a mass regime where the physics of stellar birth produces something neither planet nor star, but a curious intermediate state that will persist long after the last true stars have exhausted their fuel. The critical threshold lies at approximately 75 Jupiter masses, or roughly 0.075 solar masses. Below this limit, the core temperature and pressure never reach the 10 million Kelvin required to sustain the proton-proton chain reaction that powers hydrogen-burning stars. A brown dwarf of 50 Jupiter masses might briefly fuse deuterium in its core, a reaction requiring only about 1 million Kelvin. But deuterium constitutes merely 15 parts per million of primordial hydrogen, and this fuel exhausts itself within perhaps 100 million years. The object then settles into a long, slow cooling, radiating away the gravitational energy accumulated during its formation, but generating no new energy through nuclear processes. The physics of brown dwarf interiors differs fundamentally from that of true stars. While a red dwarf maintains itself against gravitational collapse through thermal pressure, the outward push of hot gas heated by fusion, a brown dwarf relies increasingly on electron degeneracy pressure as it cools. This quantum mechanical effect, arising from the Pauli exclusion principle that forbids electrons from occupying identical quantum states, provides support independent of temperature. A brown dwarf can cool indefinitely while maintaining roughly constant radius, its electrons packed so densely that their quantum nature rather than their thermal motion resists further compression. This degeneracy support explains one of the most counterintuitive properties of brown dwarfs. Objects spanning a factor of 10 in mass, from roughly 13 Jupiter masses to 75 Jupiter masses, all share approximately the same radius, roughly that of Jupiter itself. A brown dwarf of 70 Jupiter masses is no larger than one of 15 Jupiter masses. The additional matter simply compresses the core to higher densities. The central density of a massive brown dwarf reaches perhaps 1,000 grams per cubic centimeter, comparable to the core of our Sun. Yet the temperature remains too low for sustained fusion. The surface temperatures of brown dwarfs span an enormous range, from approximately 2,500 Kelvin for the youngest and most massive examples to below 300 Kelvin for the oldest and least massive, cooler than many planetary surfaces. Astronomers classify these objects using spectral types that extend beyond the traditional stellar sequence. L dwarfs with temperatures between 1,300 and 2,500 Kelvin, T dwarfs between 600 and 1,300 Kelvin, and the coldest Y dwarfs below 600 Kelvin. The nearest known brown dwarf, Lumen 16, lies just 6.5 light-years from Earth, and consists of a binary pair with temperatures around 1000 Kelvin, glowing dimly in infrared wavelengths invisible to human eyes. The atmospheres of these cooling objects develop remarkable complexity as temperature drops. Unlike the relatively simple hydrogen-helium envelopes of hot stars, brown dwarf atmospheres condense exotic clouds of iron droplets, silicate grains, and eventually water ice and ammonia crystals as cooling progresses. A brown dwarf at 2000 Kelvin might rain molten iron from clouds of vaporized metal. One at 1000 Kelvin develops weather patterns driven by silicate cloud formation, and the coldest examples host water clouds not unlike those of giant planets. These atmospheric dynamics produce variability in brightness as cloud patterns rotate in and out of view, weather systems on objects that will persist for cosmological timescales. The population of brown dwarfs in the Milky Way likely rivals or exceeds the number of hydrogen-burning stars. Current estimates suggest between 25 and 100 billion brown dwarfs in our galaxy alone, formed through the same gravitational fragmentation of molecular clouds that produces true stars. The initial mass function, the distribution of masses among newly formed objects, appears to continue smoothly across the stellar-substellar boundary, with low-mass objects outnumbering high-mass ones according to a power law. For every solar mass star that forms, perhaps 5 to 10 brown dwarfs emerge from the same molecular cloud complex. As the universe ages and star formation ceases, this population of brown dwarfs will continue cooling along predictable trajectories. A brown dwarf of 50 Jupiter masses, formed today with an initial surface temperature of perhaps 2500 Kelvin, will cool to 1000 Kelvin within roughly 1 billion years, to 500 Kelvin within 10 billion years, and will continue fading toward the cosmic microwave background temperature over hundreds of billions of years. The cooling rate slows as the object approaches thermal equilibrium with its surroundings, following a power law that stretches the final approach to darkness across immense timescales. The luminosity of a cooling brown dwarf drops precipitously with temperature, following the Stefan Boltzmann law that relates radiated power to the fourth power of surface temperature. A brown dwarf at 1000 Kelvin radiates roughly 100,000 times less energy than the Sun. One at 300 Kelvin radiates 10 million times less. These objects become effectively invisible at optical wavelengths, detectable only through their faint infrared glow or their gravitational influence on nearby objects. In the far future, brown dwarfs will constitute a vast population of dark, warm objects drifting through galaxies that have long since ceased producing new light. Below the brown dwarf mass range lie the planetary mass objects, bodies of less than 13 Jupiter masses that never achieve even deuterium fusion. These objects, whether formed through gravitational collapse like their more massive cousins or through planetary accretion in circumstellar disks, follow similar cooling trajectories but start from lower initial temperatures. A 5 Jupiter mass object formed in isolation might begin with a surface temperature of 1500 Kelvin, and cool to planetary temperatures within a few 100 million years. The distinction between the lowest mass brown dwarfed and the highest mass planets blurs at this boundary, defined more by formation mechanism than by any sharp physical transition. The gravitational binding energy that powers brown dwarf luminosity represents a finite reservoir. A brown dwarf of 50 Jupiter masses contains roughly 10 to the 43rd joules of gravitational potential energy, accumulated during its contraction from a diffuse cloud to a degenerate sphere. This energy radiates away at a rate determined by the object's surface temperature and area, a process that cannot be reversed without external energy input. Unlike stars, which convert mass to energy through fusion and can maintain luminosity for billions or trillions of years, brown dwarfs simply release their formation energy and fade. In the far future, as the last red dwarfs exhaust their hydrogen and transition to helium-white dwarfs, the brown dwarf population will continue its patient cooling. These objects will outlast the stars, not through any special longevity mechanism, but simply because they never truly ignited. They have no fuel to exhaust, no fusion process to terminate. A brown dwarf formed in the present epoch will still exist as a recognizable object in 10 trillion years, cooled to perhaps 50 Kelvin above the cosmic background temperature. A dark sphere of degenerate hydrogen and helium drifting through a universe grown dim. The ultimate fate of brown dwarfs depends on processes operating over timescales far longer than stellar evolution. Proton decay, if it occurs at rates suggested by grand unified theories, would gradually dissolve the nuclei that compose these objects over perhaps 10 to the 37th years. Gravitational encounters with other stellar remnants would occasionally eject brown dwarfs from their parent galaxies or send them plunging into central black holes. But on timescales of mere trillions of years, brown dwarfs represent remarkably stable configurations, quantum mechanically supported spheres of cold matter, the dimmest embers of a cosmos that once blazed with stellar fire. While these dim embers drift through the galactic disk, the Milky Way itself is not stationary in the cosmic web. Our galaxy moves through space at approximately 600 kilometers per second relative to the cosmic microwave background. But a far more consequential motion draws it toward a neighboring spiral, some 2.5 million light-years distant. The Andromeda Galaxy, designated Messier 31, approaches the Milky Way at roughly 110 kilometers per second, closing the gap between these two island universes by about 400,000 kilometers every hour. This approach has been measured through the blue shift of Andromeda's light, one of the few galaxies whose spectral lines shift toward shorter wavelengths rather than away, indicating motion toward rather than away from our position. The gravitational attraction between these two massive spirals, each containing several 100 billion stars and embedded in dark matter halos extending perhaps 1 million light-years in diameter, has been drawing them together since long before either galaxy achieved its current form. In approximately 4.5 billion years, this gravitational courtship will culminate in direct collision. The term collision, however, requires careful interpretation when applied to galaxies. Despite the hundreds of billions of stars in each system, the spaces between those stars are so vast that direct stellar impacts will be extraordinarily rare. The average separation between stars at the Milky Way's disk is roughly 4 light-years, approximately 40 trillion kilometers. If the Sun were reduced to the size of a grain of sand, the the nearest neighboring grain would sit some 5 kilometers distant. When two such sparse systems interpenetrate, their stellar populations pass through each other like two swarms of gnats, the individual members separated by distances so enormous that gravitational deflections far outweigh any possibility of physical contact. What will collide, dramatically and consequentially, are the gravitational fields themselves. The dark matter halos surrounding each galaxy, invisible scaffolding that outweighs the visible matter by roughly 5 to 1, will interact through gravity alone, their mutual attraction warping the trajectories of everything embedded within them. The stellar disks, those elegant spiral structures that define each galaxy's visible appearance, will be torn apart by tidal forces as the two systems interpenetrate. Computer simulations of this merger, run on supercomputers capable of tracking the gravitational interactions of millions of particles, reveal a complex choreography unfolding over roughly 2 billion years. The initial approach will bring the two galactic cores within perhaps 100,000 light-years of each other, close enough for tidal forces to begin distorting the spiral arms. Long streamers of stars will be pulled outward from each disk, forming what astronomers call tidal tails, bridges of stellar material stretching hundreds of thousands of light-years into intergalactic space. The first close passage will not result in immediate merger. Instead, the two galaxies will swing past each other, their mutual gravity slowing their separation, but not halting it entirely. They will recede to perhaps 300,000 light-years before falling back together for a second encounter. This gravitational dance will repeat several times over the following billion years, each passage drawing more energy from the orbital motion and converting it into the random motions of individual stars. The elegant spiral patterns that currently define both galaxies will be progressively erased, their ordered rotation replaced by chaotic stellar orbits. The gas content of each galaxy will behave quite differently from the stars. While stellar collisions remain vanishingly rare, gas clouds can and will collide directly. When molecular clouds from the Milky Way encounter those from Andromeda at relative velocities of several hundred kilometers per second, the resulting shocks will compress the gas to densities far exceeding those in normal interstellar space. This compression will trigger intense bursts of star formation, episodes of stellar birth far more vigorous than anything occurring in either galaxy today. These collision-induced starbursts will light up the merging system with the blue-white brilliance of massive young stars. For perhaps 100 million years, the combined galaxy will blaze with stellar nurseries, forming stars at rates 10 or even 100 times the current Milky Way rate of roughly 1 to 2 solar masses per year. The most massive of these new stars will live fast and die young, exploding as supernovae within a few million years of their formation and enriching the surrounding gas with heavy elements forged in their cores. But this burst of stellar fertility will accelerate the depletion of the very gas that fuels it. The merger will consume in a few 100 million years gas reserves that might otherwise have sustained star formation for billions of years. Some gas will be heated to temperatures exceeding 1 million Kelvin by supernova shocks and the energy released during the collision, expanding outward from the merged system and escaping into intergalactic space. Other gas will fall inward toward the combined galactic center, feeding the supermassive black holes that anchor each galaxy's core. The Milky Way's central black hole, Sagittarius A star, currently contains roughly 4 million solar masses. Andromeda's central black hole is considerably larger, with mass estimates ranging from 100 million to 200 million solar masses. As the merger progresses and gas funnels toward the combined center, both black holes will grow through accretion. Eventually, over perhaps 10 to 100 million years following the final coalescence of the stellar populations, these two supermassive black holes will spiral together through a process called dynamical friction, transferring their orbital energy to surrounding stars until they merge in a cataclysmic event, releasing gravitational waves detectable across the observable universe. The final product of this merger will bear little resemblance to either parent galaxy. The spiral structures will be gone entirely, replaced by a smooth elliptical distribution of stars on randomly oriented orbits. Astronomers have dubbed this future galaxy Milkomeda, though some prefer Milkdromeda, a name acknowledging both progenitors while recognizing that neither will survive in recognizable form. The merged system will contain roughly 1 trillion stars, though many of these will be the dim red dwarfs and cooling remnants discussed in previous passages. Our own solar system, if it still exists at the time of the merger, will likely survive the collision itself. The probability of another star passing close enough to gravitationally disrupt the planetary orbits is less than 1 in 100,000. However, the Sun will have long since exhausted its hydrogen fuel by this time, having expanded into a red giant approximately 5 billion years from now, and subsequently shed its outer layers to leave behind a cooling white dwarf. The Earth, if not engulfed during the red giant phase, will orbit this stellar remnant as a frozen, airless world. The merger will scatter some stars into the intergalactic void through gravitational interactions during the chaotic coalescence. Perhaps 10 to 20% of the combined stellar population will be ejected onto hyperbolic trajectories, escaping the merged system entirely to drift through the cosmic web as isolated wanderers. These ejected stars will carry with them any planetary systems they possess, creating island worlds separated from any galaxy by millions of light years of empty space. The Milkomeda merger represents just one event in a larger pattern of gravitational consolidation occurring throughout the local group. The collection of roughly 80 galaxies gravitationally bound to the Milky Way Andromeda system. The Triangulum galaxy, a smaller spiral containing roughly 40 billion stars, may be captured by the merged system or may have already merged with Andromeda before the primary collision occurs. The numerous dwarf galaxies orbiting both spirals will be absorbed over billions of years, their stars stripped away by tidal forces and incorporated into the growing elliptical. Over timescales of 100 billion years, gravitational interactions will consolidate most of the local group's mass into a single giant elliptical galaxy. But by this time, the accelerating expansion of the universe, driven by the mysterious dark energy that constitutes roughly 68% of the cosmos's energy content, will have carried all other galaxy groups beyond the cosmic horizon. The local group, merged into a single system, will find itself alone in an observable universe grown dark and empty. The light from distant galaxies redshifted beyond detection as space itself stretches faster than photons can traverse it. Within this isolated elliptical remnant, now containing perhaps 1 trillion stars drawn from the merged galaxies of the former local group, a far slower process begins to reshape the stellar distribution. Gravitational scattering, the cumulative effect of countless close encounters between stars, will gradually redistribute energy among the stellar population, a process governed by the same statistical mechanics that drives gas molecules toward thermal equilibrium. When 2 stars pass near each other, their mutual gravitational attraction deflects their trajectories. In most encounters, the deflection is slight, a gentle curve in paths that would otherwise be straight lines through the galactic potential. But over billions of years, these small deflections accumulate. Each encounter transfers a tiny amount of kinetic energy between the participants, and the statistical tendency of these transfers follows a predictable pattern. Energy flows from the more massive, slower-moving stars toward the less massive, faster-moving ones. This process, called dynamical relaxation, operates on a characteristic timescale that depends on the stellar density and velocity dispersion of the system. For a galaxy like the merged Milkomeda, with stars separated by average distances of several light-years and moving at velocities of roughly 200 kilometers per second, the relaxation time stretches to approximately 10 to the 19th years, 10 quintillion years, or about 1 billion times the current age of the universe. The mathematics of this process emerges from the Fokker-Planck equation, which describes how the distribution of stellar velocities evolves under the influence of many weak gravitational encounters. The equation reveals that the stellar system will gradually evolve toward a state of energy equipartition, where each star carries kinetic energy proportional to its mass. But this equilibrium can never be fully achieved, because the galaxy is not a closed system. Stars can escape. As relaxation proceeds, some stars gain enough velocity to exceed the escape speed from the galactic potential. For the merged elliptical galaxy, this escape velocity near the center might be 800 kilometers per second or more, but it decreases with distance from the core. Stars in the outer regions, where the gravitational binding is weaker, require less energy to break free. Through the random walk of gravitational encounters, a steady trickle of stars will achieve escape velocity and drift away into intergalactic space. The evaporation rate depends on the structure of the galaxy. Numerical simulations suggest that a typical stellar system loses roughly 1% of its mass per relaxation time through this process. For Milkomeda, this means that over 10 to the 19th years, the galaxy will shed approximately 10 billion stars into the void. These ejected stars carry away energy, causing the remaining system to contract and become more tightly bound. A counterintuitive result where losing mass makes the survivor more compact. This contraction has profound consequences. As the galaxy shrinks, stellar densities in the core increase, which shortens the local relaxation time. The core evolves faster than the outer regions, creating a runaway process called core collapse. The central density rises, encounters become more frequent, and energy flows outward more rapidly. Left unchecked, this process would drive the core toward infinite density in finite time, a mathematical singularity called the gravothermal catastrophe. But nature provides a safety valve. As the core contracts, the probability of close stellar encounters increases dramatically. When two stars pass within a few stellar radii of each other, they can form a gravitationally bound binary system, releasing binding energy in the process. This energy heats the surrounding stars, halting the collapse and even reversing it temporarily. The core oscillates between contraction and expansion, regulated by binary formation and hardening. Binary hardening occurs when a third star encounters an existing binary system. In these three-body interactions, the binary typically becomes more tightly bound. Its two components orbit closer together, while the interloper carries away the released energy. Each such encounter extracts binding energy from the binary and deposits it as kinetic energy in the surrounding stellar population. A single hard binary can heat the galactic core for millions of relaxation times, serving as a gravitational furnace that powers the galaxy's long-term evolution. The stellar types participating in this cosmic dance change as the eons pass. By 10 to the 13th years, the last red dwarfs will have exhausted their hydrogen fuel, leaving behind only stellar remnants: white dwarfs, neutron stars, and black holes. These compact objects continue to participate in gravitational scattering, but their interactions carry additional possibilities. When two white dwarfs pass close enough, tidal forces can strip material from their surfaces. When neutron stars encounter each other, gravitational wave emission can drain orbital energy, potentially leading to mergers. Black holes play a particularly important role in the long-term dynamics. Stellar mass black holes, typically 5 to 20 times the mass of the Sun, are the most massive common objects in the stellar population. Through dynamical friction, the gravitational drag experienced by massive objects moving through a sea of lighter ones, these black holes gradually sink toward the galactic center. Over timescales of 10 to the 17th years, most stellar mass black holes will have migrated to the core, where they form a dense cluster around the central supermassive black hole. The supermassive black hole at the center of Milkomeda, formed from the merger of Sagittarius A star and the black hole at Andromeda's core, will have a mass of roughly 10 million solar masses. This gravitational anchor dominates the dynamics of the inner galaxy, creating a region where stellar velocities reach thousands of kilometers per second. Stars passing too close to this central monster risk tidal disruption, being torn apart by differential gravitational forces or direct capture, spiraling inward to add their mass to the growing black hole. As tens of quintillions of years pass, the galaxy slowly evaporates from the outside in. The outer halo thins as stars escape into the growing void between galaxies. The intermediate regions gradually deplete as relaxation drives stars either inward toward the core or outward toward escape. The core itself remains dense, but slowly feeds its contents to the central black hole through a combination of tidal disruptions, gravitational wave inspirals, and direct plunges. By 10 to the 19th years, the original trillion-star galaxy will have been reduced to perhaps 1% of its initial population. The survivors cluster in a compact remnant around the supermassive black hole, a dense stellar system perhaps only a few thousand light-years across. The ejected 99% drift through intergalactic space as isolated wanderers, separated from their nearest neighbors by millions of light-years, their feeble light, by now only the thermal glow of cooling white dwarfs and neutron stars, invisible against the cosmic background. These solitary remnants trace lonely paths through an expanding universe grown vast beyond comprehension. The cosmic horizon, which today lies roughly 46 billion light-years away, will have receded to distances measured in numbers too large for intuition. Each stellar corpse occupies its own observable universe, causally disconnected from all others, drifting through darkness toward an equilibrium that lies countless eons in the future. The cosmos has entered a new epoch, one measured not in billions, but in trillions and quadrillions of years. The degenerate era unfolds across timescales that dwarf the entire previous history of the universe by factors of millions, a vast stretch of cosmic time during which no new stars will ignite, no fusion reactions will illuminate the darkness, and the only sources of energy are the slow thermal radiation of cooling stellar corpses. By approximately 10 to the 14th years after the Big Bang, 100 trillion years, or roughly 7,000 times the current age of the universe, the last red dwarf will have exhausted its hydrogen fuel. These patient stellar furnaces, some burning for 10 trillion years or more, will finally complete their nuclear burning and contract into helium-white dwarfs. Unlike their more massive predecessors that produced carbon-oxygen cores, these smallest stars lack sufficient gravitational pressure to ignite helium fusion. They simply cool, their surfaces transitioning from the dim red glow of their main sequence lives to ever fainter infrared emission. The universe at this epoch contains three primary classes of stellar remnant. White dwarfs, the most numerous, number perhaps 400 billion within the gravitationally bound core of what was once the local group's merged galaxies. These crystalline spheres, typically containing between 0.5 and 1.4 solar masses compressed into volumes roughly Earth-sized, possess initial surface temperatures ranging from 8,000 to 40,000 Kelvin, depending on their formation epoch. Their cooling follows a well-understood trajectory governed by their heat capacity and surface luminosity. A white dwarf radiates energy from its surface, according to the Stefan Boltzmann law, emitting power proportional to the fourth power of its temperature and its surface area. A typical carbon-oxygen white dwarf with a mass of 6/10 of a solar mass and a radius of approximately 9,000 kilometers possesses a surface area of roughly 1 billion square kilometers. At a surface temperature of 10,000 Kelvin, such an object radiates approximately 3 times 10 to the 24th watts, roughly 1% of the sun's current luminosity. But as it cools, this output diminishes rapidly. The cooling timescale depends critically on the white dwarf's internal structure. These objects are supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. Electrons, being fermions, cannot occupy identical quantum states, and when compressed to the densities found in white dwarf interiors, approximately 1 million grams per cubic centimeter, they form a degenerate gas whose pressure depends only on density, not temperature. This means the star can cool without contracting, slowly radiating away its thermal energy while maintaining constant size. The thermal energy stored in a white dwarf resides primarily in the ion lattice of its crystallized core. As the interior cools below approximately 6,000 Kelvin, the carbon and oxygen ions arrange themselves into a crystalline structure, releasing latent heat that temporarily slows the cooling process. This crystallization front propagates outward over billions of years, and the gravitational settling of heavier elements like neon and magnesium releases additional energy through a process called gravitational sedimentation. After 1 quadrillion years, 10 to the 15th years, the oldest white dwarfs will have cooled to surface temperatures below 1,000 Kelvin. Their peak emission will have shifted deep into the infrared, with wavelengths around 3 micrometers. Their luminosities will have fallen to roughly 10 to the -8th solar luminosities, making them nearly invisible even at close range. A white dwarf at this temperature, viewed from a distance of 1 astronomical unit, would appear as a dim ember, barely distinguishable from the cosmic microwave background, which by this epoch will have cooled to temperatures below 10 to the -12 Kelvin due to cosmic expansion. The neutron stars present in this degenerate cosmos follow their own cooling trajectory. These objects, containing between 1 and 2 solar masses compressed into spheres roughly 20 kilometers in diameter, possess initial temperatures of several hundred billion Kelvin at their formation. However, they cool rapidly through neutrino emission during their first million years, then more slowly through photon radiation from their surfaces. By the degenerate era, the oldest neutron stars will have cooled to temperatures comparable to the white dwarfs, a few thousand Kelvin or less. The internal structure of a cooling neutron star presents exotic physics. The outer crust, perhaps 1 kilometer thick, consists of a lattice of neutron-rich nuclei embedded in a sea of degenerate electrons. Deeper, the inner crust contains nuclei so neutron-rich they drip free neutrons, creating a superfluid neutron gas interpenetrating the nuclear lattice. The core, comprising the inner 10 kilometers, contains matter at densities exceeding nuclear density, roughly 2.8 times 10 to the 14th grams per cubic centimeter, where neutrons, protons, and electrons exist in beta equilibrium, possibly alongside more exotic particles like hyperons or deconfined quarks. The magnetic fields of these neutron stars, initially reaching 10 to the 12th or even 10 to the 15 Gauss for magnetars, have long since decayed through ohmic dissipation in the crust. By 10 to the 15th years, typical surface fields have fallen below 10 to the 6th Gauss, comparable to strong laboratory magnets on Earth. Without strong magnetic fields, these objects no longer produce the radio emission or X-ray pulses that once made pulsars detectable across galactic distances. Black holes constitute the third major population of the degenerate era. Within the bound remnant of the former local group, perhaps 10 billion stellar mass black holes drift through the darkness, each containing between 3 and 100 solar masses. These objects, formed from the core collapse of massive stars during the stelliferous era, emit no thermal radiation of their own. They are detectable only through their gravitational effects or on timescales far longer than the current epoch, through the quantum mechanical process of Hawking radiation. The supermassive black holes that once anchored galactic nuclei have grown through mergers during the galactic collision epoch. The central black hole of the merged system likely contains several 100 billion solar masses, having consumed the 4 million solar mass black hole from the Milky Way's center, the 100 million solar mass black hole from Andromeda, and numerous smaller black holes scattered throughout the merged stellar populations. This behemoth sits at the gravitational center of the bound stellar remnant, slowly accreting any matter that wanders within its gravitational influence. The space between these remnants has grown vast beyond comprehension. The bound core of the former local group, now containing perhaps 10 billion stellar corpses after gravitational evaporation, has ejected 99% of the original population, spans only a few thousand light-years. Yet the cosmic horizon has expanded to distances measured in numbers that strain notation. The observable universe, which today spans roughly 93 billion light-years, will have grown by factors determined by the exponential expansion driven by dark energy. Within this darkness, the stellar remnants drift in gravitational equilibrium. Their random velocities, perhaps a few hundred kilometers per second, balanced against the collective gravitational pull of the bound system. Occasional close encounters between white dwarfs or neutron stars produce gravitational perturbations, slowly redistributing energy among the population. These interactions occur with decreasing frequency as the system relaxes toward its minimum energy configuration, the stellar corpses settling into ever more circular orbits around the common center of mass. The temperature of these remnants continues to fall. After 10 to the 16th years, the oldest white dwarfs will have cooled below 100 Kelvin, colder than the surface of Pluto today. Their crystalline interiors, now nearly isothermal, radiate the last vestiges of their formation energy at wavelengths measured in tens of micrometers. The distinction between white dwarf and surrounding space becomes increasingly subtle, defined only by the slight density enhancement of the degenerate matter against the near-perfect vacuum of intergalactic space. Yet amid this cooling population of stellar corpses, another class of objects follows a different thermodynamic trajectory. Black holes, unlike white dwarfs and neutron stars, do not radiate their internal energy into space. They possess no surface temperature in the conventional sense, no crystalline lattice slowly releasing stored heat. Instead, these gravitational singularities interact with the universe through a far more selective mechanism, the capture and consumption of matter that ventures too close to their event horizons. The black holes scattered throughout the merged Milkomeda remnant represent a diverse population. Stellar mass black holes, formed from the gravitational collapse of massive stars during the Stelliferous era, typically contain between 5 and 50 solar masses. These objects measure only tens of kilometers across. A black hole of 10 solar masses possesses an event horizon with a radius of approximately 30 kilometers, smaller than many cities on the ancient Earth. Yet, despite their compact dimensions, these objects will play an increasingly prominent role as the degenerate era unfolds. The physics of black hole growth begins with the concept of the event horizon itself. This mathematical boundary marks the radius at which the escape velocity equals the speed of light, approximately 3 kilometers per solar mass of the black hole. Any matter crossing this threshold becomes permanently incorporated into the black hole's mass, adding to its gravitational influence and slightly expanding its event horizon. The process appears deceptively simple, yet the mechanics of matter capture involve some of the most extreme physics in the universe. When gas or debris approaches a black hole, it rarely falls directly inward. Conservation of angular momentum causes the material to spiral into an accretion disk, a flattened structure of orbiting matter that gradually loses energy through friction and viscous interactions. In the disk's innermost regions, temperatures can exceed 10 million Kelvin as gravitational potential energy converts to thermal radiation. The efficiency of this process is remarkable. Accretion onto a black hole can convert up to 40% of the infalling mass into radiated energy, compared to less than 1% for nuclear fusion in stellar cores. However, in the degenerate era, such vigorous accretion becomes increasingly rare. The interstellar medium has been largely consumed or expelled during the final epochs of star formation. The remaining gas exists at extraordinarily low densities, perhaps only a few hundred particles per cubic meter in the densest regions. Black holes drifting through this tenuous medium capture matter through a process called Bondi-Hoyle accretion, named for the physicists who first described the gravitational focusing of gas onto a moving point mass. The rate of Bondi-Hoyle accretion depends on the black hole's mass, its velocity relative to the surrounding medium, and the density and temperature of that medium. For a 10 solar mass black hole moving at 30 kilometers per second through gas, with a density of 100 particles per cubic centimeter and a temperature of 100 Kelvin, the accretion rate amounts to approximately 10 to the negative 18 solar masses per year. At this rate, the black hole would require 10 to the 18th years, a billion years, to double its mass through gas capture alone. This glacial growth rate ensures that stellar mass black holes remain essentially unchanged through most of the degenerate era. Their masses increase by negligible fractions, their event horizons expanding by mere millimeters over timescales that dwarf the current age of the universe by factors of billions. The accretion disks that form around them, when they form at all, glow with temperatures measured in hundreds of Kelvin rather than millions. Faint infrared sources barely distinguishable from the cooling white dwarfs that drift through the same stellar graveyard. Yet another pathway to black hole growth exists, one that operates independently of the ambient gas density. Black hole mergers occur when two of these gravitational welds encounter each other closely enough to form a bound binary system, then spiral together through the emission of gravitational waves. This process, first directly detected by the LIGO Observatory in 2015, represents one of the most energetic events in the universe. A merger of 230 solar mass, black holes releases more energy in gravitational waves during its final second than all the stars in the observable universe emit in light during that same interval. The formation of black hole binaries in the degenerate era proceeds through gravitational scattering, the same process that gradually ejects stars from the galactic remnant. When three black holes interact gravitationally, the typical outcome leaves two in a bound orbit, while the third escapes with increased velocity. The bound pair then loses orbital energy through gravitational wave emission, a process described by Einstein's general relativity. The timescale for this inspiral depends sensitively on the initial separation, a binary with components separated by 1 astronomical unit, requires approximately 10 to the power of 10/15 years to merge, while one separated by 100 astronomical units needs 10 to the 21st years. As the degenerate era progresses, these mergers gradually consolidate the black hole population. Each merger produces a single black hole with a mass slightly less than the sum of its progenitors. Typically 5 to 10% of the total mass radiates away as gravitational waves during the final coalescence. The merged remnant receives a gravitational recoil kick from asymmetric wave emission, potentially reaching velocities of several hundred kilometers per second. Some merged black holes escape the galactic remnant entirely, joining the expanding halo of ejected stellar corpses. At the center of the Milkomeda remnant, a far more massive object continues its own growth. The supermassive black hole formed from the merger of Sagittarius A star and Andromeda's central black hole contains approximately 10 billion solar masses, with an event horizon spanning some 30 billion kilometers, roughly twice the diameter of Neptune's orbit around the ancient Sun. This gravitational behemoth captures matter and smaller black holes that wander too close to the galactic core, growing incrementally over timescales measured in quadrillions of years. The supermassive black hole's sphere of influence extends across several hundred light-years, a region where its gravitational pull dominates over the collective attraction of surrounding stellar remnants. Objects passing through this zone experience tidal forces that can disrupt even the dense matter of white dwarfs, shredding them into streams of degenerate material that spiral inward over thousands of years. These tidal disruption events produce brief flares of radiation as the stellar debris forms a temporary accretion disk, momentary beacons in an otherwise darkening cosmos. These tidal disruption events, however, represent only temporary interruptions in a far more profound transformation that awaits all matter in the universe. For while black holes grow through accretion and merger, the very substance they consume, the protons and neutrons that constitute ordinary matter, may not endure forever. Deep within the theoretical framework of particle physics lies a prediction that challenges our intuition about the permanence of matter itself. The proton, that fundamental building block of atomic nuclei, has long been considered stable. In the standard model of particle physics, protons do not decay because baryon number, a quantum property that counts the total number of protons and neutrons minus antiprotons and antineutrons, is perfectly conserved. A proton cannot simply vanish or transform into lighter particles without violating this conservation law. Experimental searches have confirmed this stability to extraordinary precision, establishing that the proton lifetime exceeds 10 to the 34th years, a number so vast it dwarfs the current age of the universe by a factor of more than 10 to the 24th. Yet the standard model, for all its predictive success, is known to be incomplete. Grand unified theories, developed in the 1970s and refined in subsequent decades, propose that the three fundamental forces governing particle interactions, the strong nuclear force, the weak nuclear force, and electromagnetism, were once unified as a single force at extremely high energies. These theories predict that at energy scales around 10 to the 15th giga-electron volts, roughly 1 trillion times higher than those achieved in particle accelerators, the distinction between quarks and leptons dissolves. Particles that mediate interactions between these families, called X and Y bosons, would allow quarks to transform into leptons and vice versa. The existence of these hypothetical bosons carries a profound implication. If quarks can transform into leptons, then protons, composed of 2 up quarks and 1 down quark, can decay. The most common predicted decay channel involves a proton transforming into a neutral pion and a positron. The pion, itself unstable, quickly decays into 2 gamma-ray photons. The positron eventually encounters an electron somewhere in the cosmos, and the pair annihilates into additional photons. Through this cascade, the mass energy of the proton converts entirely into radiation. Different grand unified theories predict different proton lifetimes, but most estimates cluster around 10 to the 34th to 10 to the 36th years. The simplest models, based on the symmetry group SU5, predicted lifetimes around 10 to the 31st years, but experiments at facilities like Super Kamiokande in Japan have ruled out these shorter timescales by monitoring vast tanks of ultra-pure water for the telltale flashes of Cherenkov radiation that would signal proton decay. The current experimental lower bound stands at approximately 10 to the 34th years for the pion-positron decay channel, pushing theoretical predictions toward longer lifetimes. For the degenerate era cosmos, proton decay, if it occurs, represents the ultimate dissolution of matter. Consider a white dwarf, that crystalline remnant of a sun-like star composed primarily of carbon and oxygen nuclei. Each carbon nucleus contains 6 protons and 6 neutrons, each oxygen nucleus 8 protons and 8 neutrons. A typical white dwarf of 0.6 solar masses contains roughly 10 to the 57th protons. If protons decay with a half-life of 10 to the 37th years, then after this immense interval, half of those protons will have transformed into radiation. The process unfolds with imperceptible slowness. In any given year, only about 10 to the 20th protons decay within a white dwarf. A number that sounds large but represents merely 100 trillionth of 1% of the total. Each decay releases approximately 938 mega-electron volts of energy, the rest mass of the proton converted to radiation. The cumulative effect produces a faint but steady luminosity, roughly 10 to the negative 24th solar luminosities, far dimmer than any astronomical source observable today, yet sufficient to maintain the white dwarf at a temperature slightly above absolute zero. This decay luminosity creates a curious equilibrium. As the white dwarf's thermal energy radiates away into space, proton decay replenishes it from within. The stellar corpse glows not from residual heat or gravitational contraction, but from the gradual dissolution of its own substance. The temperature stabilizes around a few hundredths of a Kelvin, maintained by this internal nuclear transmutation. Neutrons bound within nuclei face a similar fate. Free neutrons decay rapidly, with a half-life of approximately 610 seconds, transforming into protons, electrons, and antineutrinos through the weak nuclear force. But neutrons bound within stable nuclei like carbon-12 or oxygen-16 are protected from this decay by the nuclear binding energy. Grand unified theories, however, predict that bound neutrons can also decay through X-boson exchange, with lifetimes comparable to those of protons. The distinction between proton decay and bound neutron decay becomes academic over time scales of 10 to the 37th years. Both processes contribute to the gradual erosion of nuclear matter. The products of proton decay, photons, neutrinos, and the occasional electron-positron pair, carry away the mass energy of the decaying nuclei. These particles stream outward into the expanding void, their wavelengths stretching with cosmic expansion. The photons redshift toward ever lower energies, eventually becoming indistinguishable from the cosmic microwave background radiation, itself cooled to temperatures far below 1 Kelvin. The neutrinos, nearly massless and weakly interacting, pass through the remnants of matter without effect, carrying their energy toward the infinite future. As proton decay proceeds, the composition of stellar remnants transforms. White dwarfs, initially composed of carbon and oxygen, gradually lose mass as their nuclei dissolve. After 10 to the 38th years, a significant fraction of the original matter has converted to radiation. The crystalline lattice structure, maintained by electrostatic repulsion between nuclei, begins to fail as the nuclear density decreases. The white dwarf does not collapse. There is insufficient mass remaining to overcome electron degeneracy pressure, but rather disperses, its remaining matter spreading into an ever more diffuse cloud of surviving nuclei, electrons, and decay products. Neutron stars undergo an analogous dissolution, though their internal structure complicates the process. The neutron-rich matter in a neutron star's core exists at densities exceeding 10 to the 17th kilograms per cubic meter, where nuclear matter merges into a continuous fluid rather than discrete nuclei. Proton decay in this environment proceeds through the same fundamental mechanism, but manifests differently, gradually converting the neutron star's mass into radiation, while the immense gravitational field prevents rapid dispersal of the remaining matter. The timescale of proton decay, 10 to the 34th years or longer, exceeds even the vast epochs required for stellar remnants to cool to near absolute zero. By the time proton decay becomes the dominant process affecting matter, the universe has aged for quadrillions of years. The cosmic expansion has stretched space to unimaginable scales, with the observable universe extending across distances measured in numbers that exhaust conventional notation. Former galaxy clusters have long since dispersed, their constituent remnants scattered across voids so vast that light requires times comparable to the proton lifetime to traverse them. In this epoch, the universe contains three categories of objects: black holes, which do not undergo proton decay because their matter has collapsed beyond the event horizon; stellar remnants slowly dissolving through nuclear transmutation; and the diffuse radiation bath of photons and neutrinos produced by countless decay events. The relative importance of these components shifts as proton decay proceeds. Matter, once the dominant form of cosmic structure, gradually converts to radiation, rejoining the primordial photons and neutrinos that have filled the universe since its earliest moments. The iron cores of ancient white dwarfs, those crystalline spheres that once represented the endpoint of stellar nucleosynthesis, now face their own dissolution. Iron 56, with its 26 protons and 30 neutrons, possesses the highest binding energy per nucleon of any element, which is precisely why stellar fusion halts when iron accumulates in massive star cores. No energy can be extracted by fusing iron into heavier elements, yet this nuclear stability, so absolute on timescales of billions of years, proves merely temporary when measured against the predictions of grand unified theories. Each iron 56 nucleus contains 26 protons, and each proton carries within it the seeds of its own eventual transformation. The decay process operates independently for each nucleon, meaning that a white dwarf containing approximately 10 to the 57th protons will experience a continuous rain of decay events throughout the proton decay era. At a half-life of 10 to the 34th years, roughly 10 to the 23rd protons decay per year within such an object. Each decay releases approximately 1 gigaelectron-volt of energy, producing a steady internal heat source that maintains the remnant at temperatures slightly above the cosmic background. This internal heating creates a peculiar thermal equilibrium. The white dwarf, long since cooled to temperatures indistinguishable from absolute zero through conventional radiative processes, now glows faintly from within. The energy released by proton decay diffuses outward through the crystalline iron lattice, emerging as thermal radiation at temperatures of perhaps a few hundredths of a Kelvin. Such temperatures seem impossibly cold by terrestrial standards, yet they represent a significant excess above the cosmic microwave background, which by this epoch has red-shifted to temperatures below 10 to the negative 15 Kelvin. The decay products themselves tell the story of matter's dissolution. When a proton within an iron nucleus decays, it typically produces a positron and a neutral pion. The positron, carrying positive charge, immediately encounters one of the many electrons still bound to the remnant's matter. This encounter results in mutual annihilation, converting the electron-positron pair into 2 gamma-ray photons, each carrying 511 kiloelectron-volts of energy. These photons scatter through the dense material, gradually thermalizing as they transfer their energy to the surrounding lattice. The neutral pion, meanwhile, lives for only 10 to the negative 16 seconds before decaying into 2 additional gamma-ray photons. These photons carry roughly 67 mega-electron-volts each, far more energetic than the annihilation radiation. They too scatter and thermalize, contributing to the internal heat budget of the dissolving remnant. The net result of each proton decay is the conversion of approximately 1 atomic mass unit of matter into electromagnetic radiation, plus a shower of neutrinos that escape immediately into the cosmic void. As protons decay within the iron nuclei, the nuclear structure becomes increasingly unstable. An iron 56 nucleus that loses a proton becomes manganese 55, which itself contains 25 protons awaiting their own eventual decay. The neutrons left behind face a different fate. Free neutrons decay through the weak nuclear force with a half-life of approximately 10 minutes, converting into protons, electrons, and antineutrinos. But neutrons bound within nuclei are stabilized by the nuclear binding energy, and they persist until the nucleus itself becomes so proton-depleted that it can no longer maintain structural integrity. This gradual nuclear dissolution transforms the crystalline iron lattice into an increasingly exotic state of matter, where once the white dwarf consisted of orderly arrays of iron nuclei embedded in a degenerate electron sea, it now contains a mixture of progressively lighter elements, free neutrons, and the radiation products of countless decay events. The electron degeneracy pressure that originally supported the remnant against gravitational collapse slowly diminishes as electrons annihilate with the positrons produced by proton decay. The timescale for complete dissolution depends on the total number of protons and the decay half-life. A white dwarf of 1 solar mass contains approximately 10 to the 57th protons. After one half-life of 10 to the 34th years, half of these protons have decayed. After 10 half-lives, or 10 to the 35th years, fewer than 1 in 1,000 original protons remain. After 30 half-lives, approximately 10 to the 37th years, the probability of finding even a single original proton approaches 0. The white dwarf has converted entirely to radiation, neutrinos, and whatever stable decay products the particular grand unified theory predicts. Neutron stars undergo a parallel dissolution, though their initial conditions differ significantly. A neutron star of 1.4 solar masses contains approximately 10 to the 57th neutrons, with only a thin crust of conventional nuclear matter. The neutrons in the stellar interior exist in a superfluid state, paired through nuclear forces into Cooper pairs, analogous to those in superconducting materials. Yet even this exotic state cannot prevent the eventual decay of the constituent nucleons. The neutron star's dissolution proceeds from the outside inward. The iron-rich crust, similar in composition to white dwarf matter, decays through the same proton decay mechanism. As the crust dissolves, the underlying neutron fluid becomes exposed to the vacuum. Free neutrons at the surface undergo beta decay on timescales of minutes, converting to protons and electrons that immediately participate in proton decay or annihilation processes. The neutron star slowly evaporates, its mass converting to radiation over timescales of 10 to the 37th years. Throughout the cosmos, this dissolution proceeds simultaneously in trillions upon trillions of stellar remnants, each cooling corpse, whether white dwarf, neutron star, or the iron-rich debris of ancient planetary systems, undergoes the same inexorable transformation. The universe's baryonic matter, forged in the first 3 minutes after the Big Bang and subsequently processed through generations of stellar nucleosynthesis, now returns to its most fundamental form, pure energy radiating into an ever-expanding void. Yet even as baryonic matter dissolves into radiation, the black holes that have grown through billions of years of accretion remain seemingly eternal. These gravitational singularities, cloaked behind event horizons from which no light escapes, appear to represent permanent features of the cosmos. A black hole, once formed, seems destined to persist forever, its mass locked away behind a one-way boundary in space-time. classical physics offers no mechanism for a black hole to lose mass or shrink. The event horizon, that mathematical surface where escape velocity equals the speed of light, appears to be an absolute barrier. But classical physics does not account for the quantum nature of the vacuum itself. In 1974, Stephen Hawking demonstrated that black holes are not truly black. They emit radiation through a subtle quantum mechanical process that operates at the event horizon, a phenomenon now known as Hawking radiation. This discovery revealed that black holes possess temperature, entropy, and finite lifespans, connecting gravitational physics to thermodynamics in ways that continue to shape our understanding of quantum gravity. The mechanism begins with the quantum vacuum, which is not truly empty. Heisenberg's uncertainty principle, that fundamental constraint on simultaneous knowledge of position and momentum, also applies to energy and time. This means that empty space cannot possess exactly zero energy for any finite duration. Instead, the vacuum seethes with virtual particle pairs, fleeting fluctuations that borrow energy from nothing, exist for impossibly brief moments, and then annihilate each other to repay the energy debt. These pairs consist of particles and their antiparticles, electrons and positrons, quarks and antiquarks, photons paired with themselves. They appear and vanish continuously throughout all of space, their existence permitted by quantum mechanics as long as their lifetimes remain shorter than approximately 10 to the negative 21 seconds, divided by their energy in electron volts. Near a black hole's event horizon, these virtual pairs encounter a unique circumstance. The gravitational field varies so steeply across the tiny distance separating the particle from its antiparticle that tidal forces can separate them before they annihilate. One member of the pair falls through the event horizon into the black hole, while its partner escapes to infinity as real radiation. The energy required to promote these virtual particles to real existence comes from the black hole's gravitational field, which means it comes from the black hole's mass. Each escaping particle carries away a tiny amount of energy, and by Einstein's mass-energy equivalence, the black hole loses a corresponding amount of mass. The temperature of this radiation depends inversely on the black hole's mass. A black hole of 1 solar mass, approximately 2 times 10 to the 30 kilograms, has a Hawking temperature of only 60 billionths of a Kelvin, 60 nanokelvin, far colder than the current cosmic microwave background temperature of 2.7 Kelvin. This means that solar mass black holes in the present universe actually gain more energy from absorbing cosmic microwave background photons than they lose through Hawking radiation. They are growing, not shrinking. Only when the universe has expanded and cooled sufficiently, when the cosmic background temperature drops below a black hole's Hawking temperature, will that black hole begin its slow evaporation. For a stellar mass black hole of 10 solar masses, the Hawking temperature is approximately 6 nanokelvin. The cosmic microwave background will not cool to this temperature until the universe is roughly 10 to the 18th years old, 1 quintillion years, 1,000,000 times the current age of the cosmos. Only then will stellar mass black holes begin their net mass loss. For the supermassive black holes at galactic centers, with masses of millions to billions of solar masses, the Hawking temperatures are correspondingly lower, 10 to the negative 14th Kelvin for a million solar mass black hole. These giants must wait until the universe is 10 to the 23rd years old before evaporation begins. The radiation spectrum emerging from a black hole follows a perfect black-body distribution, the same thermal spectrum emitted by any object in thermal equilibrium. This was one of Hawking's most profound discoveries. Black holes are thermodynamic objects with well-defined temperatures and entropies. The entropy of a black hole, as calculated by Jacob Bekenstein and confirmed by Hawking, is proportional to the area of its event horizon divided by 4 times the Planck area, where the Planck area is approximately 2.6 times 10 to the negative 70 square meters. A solar mass black hole has an entropy of approximately 10 to the 77 in natural units, vastly exceeding the entropy of any ordinary matter configuration of similar mass. The power output of Hawking radiation scales as the inverse square of the black hole's mass. A 10 solar mass black hole radiates approximately 10 to the negative 29 watts, an almost inconceivably feeble luminosity. At this rate, losing mass at 10 to the negative 29 kilograms per second, the black hole would require 10 to the 67 years to evaporate completely. This is the characteristic evaporation timescale for stellar mass black holes, a number so vast that it exceeds the current age of the universe by 57 orders of magnitude. As the black hole loses mass, its temperature rises. This creates a runaway process. Higher temperature means faster radiation, which means faster mass loss, which means even higher temperature. The evaporation accelerates continuously. A black hole that has shrunk to the mass of a mountain, approximately 10 to the 12th kilograms, has a temperature of 10 to the 11th Kelvin, hot enough to emit gamma rays. At this mass, it radiates 10 to the 10 watts, 10 billion watts, and has only minutes of existence remaining. The final moments of a black hole's life unfold in a spectacular burst. In the last second, the black hole's temperature exceeds 10 to the 13th Kelvin, hotter than any stellar core. It emits a flash of gamma rays, electrons, positrons, neutrinos, and any other particles whose rest mass energy is below the thermal energy scale. The total energy released in this final explosion equals the remaining mass times the speed of light squared, approximately 10 to the 22 joules for a black hole that has evaporated down to 10 to the 5 kilograms. Then the black hole is gone, its mass entirely converted to radiation that disperses into the expanding void. Throughout the black hole era, this process repeats across the cosmos. Stellar mass black holes, the remnants of ancient massive stars, evaporate first, their 10 to the 67-year lifespans representing the shortest timescale among black hole populations. Intermediate mass black holes, those rare objects of hundreds to thousands of solar masses formed through stellar mergers in dense clusters, persist somewhat longer. The supermassive black holes at the centers of merged galactic remnants, with masses reaching billions of solar masses, endure the longest, their evaporation timescales stretching to 10 to the 98 or 10 to the 100 years. The radiation emitted by evaporating black holes represents the final significant energy release in the universe. Long after proton decay has dissolved the last white dwarf, long after the cosmic microwave background has red-shifted to wavelengths larger than the observable universe. The faint glow of Hawking radiation continues. Each black hole serves as a slowly dimming ember, converting the gravitational energy locked within its event horizon into thermal radiation that disperses into infinite space. The universe in this era is not completely dark, but illuminated by the ghostly radiance of evaporating singularities, a radiance so feeble that a human eye, if one could exist, would detect nothing but absolute blackness. The stellar mass black holes that populate this darkened cosmos represent the first category of gravitational remnants to complete their evaporative journey. These objects, born from the collapsed cores of massive stars that exhausted their nuclear fuel in the stelliferous era, typically contain between 3 and perhaps 50 solar masses of gravitationally compressed space-time. A black hole of 10 solar masses, a common product of supernovae from progenitor stars that once burned with luminosities thousands of times greater than the Sun, possesses a Schwarzschild radius of approximately 30 kilometers. This event horizon, smaller than many asteroids that once orbited ancient planetary systems, encloses a region of space-time so severely curved that not even light can escape its gravitational embrace. The temperature of such a black hole, determined by the inverse relationship between mass and Hawking temperature, measures approximately 6 billionths of a Kelvin. This temperature, 6 times 10 to the negative 9 Kelvin, falls far below the cosmic microwave background radiation that once bathed the universe at 2.725 Kelvin in the era when stars still burned. For billions upon billions of years, these stellar mass black holes actually absorbed more energy from the cosmic background than they emitted through Hawking radiation, experiencing net growth rather than evaporation. Only when the expanding universe stretched the background radiation to temperatures below the black hole's own Hawking temperature did the evaporative process truly begin in earnest. The mathematics governing this evaporation follows a precise relationship discovered through Stephen Hawking's theoretical work in 1974. The evaporation timescales as the cube of the black hole's mass, meaning that a black hole twice as massive takes 8 times longer to evaporate completely. For a 10 solar mass black hole, this calculation yields an evaporation timescale of approximately 10 to the 67 years. Written in full, this number contains 67 zeros following the initial digit, a duration so vast that the entire previous history of the universe from the Big Bang through the stelliferous era through the degenerate era represents less than a single tick of this cosmic clock. Throughout this immense span, the black hole radiates energy at an almost imperceptibly slow rate. The luminosity of a 10 solar mass black hole through Hawking radiation measures approximately 9 times 10 to the negative 31 watts. To place this in perspective, a single human cell metabolizing glucose produces roughly 10 to the negative 12 watts of thermal energy, making even cellular metabolism a trillion times more energetic than the Hawking radiation from a stellar mass black hole. A standard 60-watt incandescent light bulb, burning for a single second, releases more energy than such a black hole emits over millions of years. The radiation itself emerges predominantly as photons, though the spectrum includes all particle species with rest masses below the black hole's characteristic temperature. For stellar mass black holes at 6 billionths of a Kelvin, only massless photons and gravitons contribute significantly to the emission. The photons emerge with wavelengths measuring approximately 50,000 kilometers, placing them firmly in the radio portion of the electromagnetic spectrum, with frequencies around 6 Hz. These extraordinarily long wavelength photons carry individual energies of merely 4 × 10 to the negative 32 joules, requiring the emission of roughly 10 to the 23 such photons to release the energy equivalent of a single visible light photon. As eons accumulate into epochs, and epochs compound into eras beyond human naming, the black hole's mass gradually diminishes. Each photon that escapes the quantum vacuum near the event horizon carries away a minuscule fraction of the black hole's total mass energy. The relationship between mass loss and time follows a differential equation whose solution reveals that the evaporation accelerates as the black hole shrinks. A black hole that has lost half its original mass will evaporate completely in only 1/8 the time it took to lose that first half. This runaway process, however, remains imperceptible across timescales that would seem eternal to any observer. After 10 to the 60 years, roughly 1,000th of the total evaporation time, the 10 solar mass black hole has lost only a negligible fraction of its original mass. The Schwarzschild radius has barely contracted, the Hawking temperature has barely increased, and the luminosity remains essentially unchanged. The universe during this phase contains countless such black holes, each radiating its feeble glow into the expanding void, each following its own trajectory toward eventual dissolution. Some stellar mass black holes formed from the first generation of massive stars, population 3 objects that ignited when the universe was merely 200 million years old, have been evaporating longer than their younger counterparts. Yet even these ancient remnants retain nearly all their original mass. The spatial distribution of these evaporating black holes reflects the gravitational dynamics that shaped the degenerate era. Many remain gravitationally bound within the remnants of ancient galaxies, orbiting common centers of mass alongside white dwarf remnants, neutron star corpses, and the supermassive black holes that once anchored galactic nuclei. Others were ejected through gravitational scattering events over the preceding 10 to the 19th years, now drifting through intergalactic space as isolated points of slowly evaporating space-time curvature. The average separation between stellar mass black holes in the remnants of galaxy clusters measures perhaps several light-years, while ejected black holes may drift for millions of light-years without encountering another massive object. Occasionally, 2 stellar mass black holes approach closely enough for gravitational wave emission to drain their orbital energy, initiating an in-spiral that culminates in merger. These events, which produced the gravitational wave signals detected by instruments like LIGO during the Stelliferous era, continue throughout the black hole era whenever chance brings 2 such objects into proximity. Each merger produces a single larger black hole with mass slightly less than the sum of its progenitors, the difference radiated away as gravitational waves that ripple outward at the speed of light. A merger of two 10 solar mass black holes produces a remnant of approximately 18 solar masses, with nearly 2 solar masses of energy converted to gravitational radiation in the final milliseconds of coalescence. These merged black holes, now more massive, face even longer evaporation timescales. An 18 solar mass black hole requires approximately 6 times 10 to the 67 years to evaporate completely, extending its existence well beyond its smaller counterparts. The hierarchical merger process can build black holes of several hundred solar masses within dense stellar remnant clusters, creating objects that will persist for 10 to the 69 or 10 to the 70 years. Yet even these enhanced lifespans represent mere moments compared to the supermassive black holes that anchor the centers of ancient galactic remnants. The final stages of stellar mass black hole evaporation unfold with increasing drama across the last fraction of their existence. When approximately 10 to the 67th years have elapsed, and the black hole has shrunk to a mass comparable to a small asteroid, roughly 10 to the 12 kilograms, the Hawking temperature rises to approximately 10 to the 11 Kelvin. At this temperature, the black hole radiates not merely radio photons, but gamma rays, electron-positron pairs, and eventually heavier particles as the temperature continues climbing. The luminosity increases from its initial 10 to the negative 31 watts to values approaching a megawatt, then a gigawatt, then the luminosity of a star. In the final second of its existence, the remaining mass converts entirely to radiation in a burst that briefly outshines the feeble glow of all other Hawking radiation in the observable universe. This terminal flash, releasing approximately 10 to the 22 joules of energy, represents the black hole's final contribution to cosmic entropy before its event horizon shrinks to the Planck scale, and quantum gravitational effects, still poorly understood by human physics, govern the ultimate fate of the singularity. Whether some remnant persists or the black hole vanishes entirely remains a question that the physics of the stelliferous era could not definitively answer. The stellar mass black holes, however, represent merely the first wave of evaporative dissolution. Far more massive objects continue their patient existence across timescales that dwarf even these astronomical durations. The supermassive black holes that once anchored galactic centers, those gravitational monarchs that grew through billions of years of accretion and merger, now drift through the emptiness as the universe's most enduring structures. Consider the black hole that once resided at the center of the Milky Way, the object astronomers designated Sagittarius A star. During the stelliferous era, this black hole contained approximately 4 million solar masses, its event horizon spanning a diameter of roughly 24 million kilometers, comparable to the orbit of Mercury around the Sun. Through the subsequent eons of galactic merger and accretion, such objects typically grew to masses between 1 billion and 100 billion solar masses. These are the titans that now populate the dark cosmos, their event horizons stretching across distances measured in hundreds of astronomical units. The mathematics of Hawking radiation reveals why these objects persist so extraordinarily long. The evaporation timescale scales with the cube of the black hole's mass. A black hole of 1 billion solar masses containing approximately 2 × 10 to the 39 kilograms, possesses an evaporation time of roughly 10 to the 92 years. Increase that mass to 100 billion solar masses, and the evaporation timescale extends to approximately 10 to the 99 years, approaching 10 to the 100th power, a number so vast that it exceeds the total count of particles in the observable universe by a factor of 10 to the 19th. The Hawking temperature of these supermassive black holes registers as almost incomprehensibly cold. A black hole of 10 billion solar masses radiates at a temperature of approximately 6 × 10 to the -18 Kelvin, more than a quadrillion times colder than the cosmic microwave background radiation was during the Stelliferous era. This temperature lies so far below any other thermal scale in physics that the black hole exists in a state of near-perfect thermodynamic isolation, its radiation output measured in units smaller than a single photon per century. The power output of such an object amounts to roughly 10 to the -52 watts, a luminosity so feeble that the total energy radiated over 1 trillion years would not suffice to warm a single atom by a measurable amount. Yet this infinitesimal trickle of radiation, sustained across timescales that reduce the current age of the universe to insignificance, eventually accomplishes what no other process can. The black hole slowly, inexorably, converts its gravitational binding energy into the entropy of dispersed radiation. The spectrum of this radiation shifts as the black hole evolves. Initially, the Hawking temperature lies so far below the rest mass energy of even the lightest particles that only gravitons and photons emerge from the quantum vacuum near the event horizon. These massless particles carry away energy in wavelengths stretching across distances comparable to the event horizon itself, radio waves of such extreme length that they would span solar systems. As the black hole shrinks over the eons, the wavelength decreases and the temperature rises, though the change proceeds so gradually that meaningful evolution requires timescales measured in powers of 10 to the 90th years. The environment surrounding these supermassive black holes during the black hole era consists of almost perfect vacuum. The matter that once formed accretion disks has long since either fallen through the event horizon or been scattered to cosmological distances. The stellar remnants that once orbited in gravitational bondage have either merged with the central black hole or been ejected through 3 body interactions over timescales of 10 to the 19th years. What remains is emptiness punctuated by the occasional passage of a relic particle, itself destined for eventual decay. The gravitational influence of these supermassive black holes extends across enormous distances even as the universe continues its accelerating expansion. The event horizon may span hundreds of astronomical units, but the gravitational sphere of influence, the region where the black hole's gravity dominates over the cosmic expansion, stretches across thousands of light years. Within this volume, any matter that wanders close enough will eventually spiral inward, adding marginally to the black hole's mass and briefly extending its evaporative lifetime. Yet such encounters grow increasingly rare as cosmic expansion dilutes the density of matter to levels approaching absolute emptiness. The average separation between supermassive black holes increases exponentially, driven by dark energy's relentless acceleration. Objects that once shared gravitational interactions across megaparsec scales now recede beyond each other's cosmological horizons, each black hole becoming an isolated island of gravitational curvature in an otherwise flat and empty space-time. The internal structure of these supermassive black holes, hidden forever behind their event horizons, remains a domain where classical general relativity breaks down and quantum gravity presumably governs. The singularity at the center, that point of theoretically infinite density, may in reality be replaced by some quantum gravitational structure, perhaps a region of Planck scale curvature, where space-time itself becomes granular. The information that fell into the black hole over billions of years of accretion, the quantum states of stars and planets and gas clouds, remains encoded in subtle correlations within the Hawking radiation, gradually released back into the universe through a process that preserves unitarity while scrambling the original data beyond any practical recovery. As the eons accumulate toward 10 to the 100th years, even these most massive black holes begin their final approach toward dissolution. The mathematics remains unchanged from their smaller cousins, merely extended across vaster timescales. The temperature rises from 10 to the -18th Kelvin toward 10 to the -15th, then 10 to the -12th. The power output increases from 10 to the -52nd watts toward values that, while still negligible by any ordinary standard, represent meaningful energy transfer on cosmological timescales. The final stages of supermassive black hole evaporation compress into a relative instant, the last 10 to the 60th years witnessing an acceleration that mirrors the death of stellar mass black holes, but begins from a far more massive starting point. The event horizon, once spanning hundreds of astronomical units, contracts through planetary scales, then stellar scales, then the dimensions of mountains and cities and grains of sand. The temperature soars through the thresholds for electron-positron production, then muon pairs, then heavier particles, until the final moments release a burst of radiation containing the entire remaining mass energy of what was once a galactic nucleus. The universe that remains after these final cataclysmic bursts enters a state unlike any that has existed before. This is the black hole era in its purest form, a cosmos where the dominant structures are not stars or galaxies or even the diffuse remnants of dissolved matter, but the gravitational singularities themselves, scattered across distances so vast that the concept of proximity loses all practical meaning. The timescales involved defy comprehension through ordinary analogies. If the entire previous history of the universe, from the Big Bang through the Stelliferous era, through the cooling of white dwarfs and the dissolution of protons, were compressed into a single second, the black hole era would stretch for billions upon billions of years at that same compressed rate. The number 10 to the 100th power, written as a 1 followed by 100 zeros, represents not merely a large number, but a duration so extreme that all previous cosmic history vanishes into insignificance beside it. During this epoch, the universe contains a hierarchy of black holes sorted by mass, and therefore by longevity. The stellar mass remnants, Those objects of 10 to perhaps 100 solar masses have long since completed their evaporative journeys. Intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses, persist somewhat longer, their Hawking temperatures measured in fractions of a nanokelvin, their luminosities so faint that detecting them would require instruments of impossible sensitivity. These objects evaporate over timescales of 10 to the 75th to 10 to the 85th years, their lifespans determined by the cube of their initial mass. The supermassive black holes, however, remain the true monarchs of this era, objects like the descendants of Sagittarius, a star grown through billions of years of galactic mergers to masses of billions or tens of billions of solar masses, emit Hawking radiation at temperatures of approximately 10 to the minus 17th Kelvin. At such temperatures, the characteristic wavelength of emitted photons exceeds the current observable universe by factors of trillions. These photons carry energies so minuscule that individual quanta represent less energy than the kinetic motion of a single atom at room temperature divided by factors exceeding 10 to the 20th power. The space between these surviving black holes has expanded to dimensions that render the concept of a universe almost meaningless in any local sense. The cosmic expansion, continuing at its accelerated rate driven by dark energy, has stretched the distances between gravitationally bound systems to scales measured in numbers that exhaust mathematical notation. Where once galaxies clustered in groups and superclusters spanning hundreds of millions of light-years, now individual black holes drift through volumes of space so large that light emitted from one would never reach another. The expansion of intervening space, outpacing even photons traveling at nature's speed limit. The cosmic microwave background radiation, that echo of the universe's fiery birth, has red-shifted to wavelengths spanning light years, its temperature fallen below 10 to the minus 30 Kelvin. This radiation, once the dominant energy content of the young universe, now represents a negligible contribution to the cosmic energy budget, itself dwarfed by the dark energy that drives continued expansion. The photons that once carried information about the universe's earliest moments have stretched beyond any possibility of detection, their wavelengths exceeding the scale of any conceivable instrument. Within this vast emptiness, the black holes themselves undergo subtle evolution. Their rotation, inherited from the angular momentum of accreted matter during the stelliferous era, gradually diminishes through a process called superradiance, where rotating black holes can shed angular momentum by amplifying certain frequencies of radiation. A maximally rotating Kerr black hole, spinning at the theoretical limit where its event horizon would become singular, slowly transfers its rotational energy into the surrounding space-time, asymptotically approaching the non-rotating Schwarzschild configuration over timescales comparable to the evaporation time itself. The geometry of space-time around these objects remains remarkable even in this desolate epoch. The event horizon of a 10 billion solar mass black hole spans approximately 60 billion kilometers, roughly 400 astronomical units, a sphere that would encompass the orbits of all planets in a solar system with room to spare. Yet this horizon represents not a physical surface, but a mathematical boundary, the point beyond which the escape velocity exceeds the speed of light, the threshold from which no signal can return to the external universe. Inside this boundary, according to general relativity, space-time curves so severely that all trajectories lead inexorably toward the central singularity, a point of theoretically infinite density where the known laws of physics cease to provide meaningful predictions. Whether quantum gravitational effects modify this classical picture, perhaps replacing the singularity with some exotic quantum state, remains unknown, the resolution of this question requiring a complete theory of quantum gravity that has eluded physicists throughout the stelliferous era and beyond. The Hawking radiation emitted by these supermassive black holes consists predominantly of photons and gravitons, the massless carriers of electromagnetic and gravitational force. Heavier particles cannot be produced because the Hawking temperature lies far below the rest mass energy of even the lightest massive particles, the electrons and positrons that would require temperatures exceeding 10 to the 9th Kelvin for thermal production. The radiation emerges not from the singularity itself, but from the quantum vacuum near the event horizon, where the intense gravitational field separates virtual particle pairs, allowing one member to escape while the other falls inward, carrying negative energy as measured from infinity. This process, though vanishingly slow, represents an irreversible transfer of mass energy from the black hole to the surrounding universe. The second law of thermodynamics, that entropy must increase in any closed system, finds its ultimate expression in black hole evaporation. The entropy of a black hole, proportional to the area of its event horizon measured in Planck units, represents the maximum entropy that can be contained within a given region of space. As the black hole evaporates, this entropy transforms into the thermal entropy of the emitted radiation, spreading irreversibly through the expanding cosmos. The final black hole, a supermassive remnant that once anchored a galaxy of hundreds of billions of stars, approaches the conclusion of its existence across timescales that render all previous cosmic history infinitesimal by comparison. This object, perhaps containing the merged mass of what were once millions of stellar mass black holes and the accumulated matter of countless galactic collisions, has persisted through epochs measured in units of 10 to the 100th power years. Its event horizon, once spanning distances comparable to our solar system, has contracted through the relentless mathematics of Hawking evaporation to dimensions that would fit within the orbit of Mercury, then within the diameter of Earth, then smaller still. The temperature of this dying giant rises inversely with its shrinking mass. Where once it radiated at temperatures of 10 to the minus 17 Kelvin, imperceptibly colder than the cosmic microwave background that has long since redshifted to effective nothingness, it now glows with increasing thermal energy. The radiation that escapes its curved space-time shifts from wavelengths longer than galaxies to wavelengths measurable in astronomical units, then in light hours, then in light minutes. Each photon carries away a fraction of the black hole's remaining mass energy, and as the mass decreases, the rate of emission accelerates according to the Stefan Boltzmann law applied to this strangest of all thermal bodies. The surrounding universe, if it could be called surrounding in any meaningful sense, consists of nothing but the most diffuse possible distribution of photons and the lightest stable particles. Electrons and positrons, the survivors of proton decay that occurred across timescales of 10 to the 34th to 10 to the 40th years, drift through volumes of space so vast that the average distance between any two particles exceeds what were once the distances between galaxy clusters. The expansion of space has stretched the cosmos to dimensions that bear no relationship to the compact, dense universe of the stelliferous era. Light emitted from one region would require times exceeding the current age of this ancient cosmos to reach any neighboring particle. Against this backdrop of absolute emptiness, the final black hole continues its transformation from gravitational singularity to pure radiation. The mathematics governing this process, first described by Stephen Hawking in 1974, reveals that the power output of an evaporating black hole scales as the inverse square of its mass. A black hole of 1 solar mass would radiate approximately 10 to the negative 28th watts, a power output so minuscule that it would take 10 to the 67th years to evaporate completely. But as the mass decreases, this power output increases dramatically. When the black hole has shrunk to the mass of a large asteroid, perhaps 10 to the 15th kilograms, it radiates with the power of a small star. When it reaches the mass of a mountain, 10 to the power of 12 kilograms, its luminosity exceeds that of the sun. The final stages of black hole evaporation unfold with increasing rapidity, a cosmic acceleration after eons of imperceptible change. In the last second of its existence, the black hole releases energy equivalent to millions of nuclear weapons, a burst of gamma radiation and particle-antiparticle pairs that propagates outward at the speed of light through the empty cosmos. The temperature of the Hawking radiation in these final moments exceeds 10 to the 12th Kelvin, hot enough to produce quarks and gluons, the fundamental constituents of matter that have not existed freely since the first microseconds after the Big Bang. This final explosion, though energetic by any standard of the stelliferous era, disperses into a universe so vast that its effects become unmeasurable within cosmologically insignificant distances. The photons produced in this terminal burst join the diffuse background of radiation that permeates all of space, their energy gradually redshifting as the universe continues its eternal expansion. The particles created in the explosion, electrons and positrons and neutrinos, scatter into the void, adding infinitesimally to the sparse population of matter that drifts through the darkness. The event horizon, that mathematical boundary from which nothing could escape, shrinks through its final dimensions. It passes through the Schwarzschild radius corresponding to the mass of a human being, approximately 10 to the minus 23 meters, smaller than an atomic nucleus. It contracts through scales where quantum gravitational effects, described by theories not yet fully understood, become dominant. The classical description of space-time curvature breaks down as the black hole approaches the Planck mass of approximately 2.2 times 10 to the negative 8th kilograms, where gravitational and quantum effects become comparable in strength. In these final moments, the black hole exists in a regime where no current physical theory provides complete guidance. The singularity at its center, that point of theoretically infinite density, where the known laws of physics fail, approaches its dissolution. Whether information that fell into the black hole over its immense lifetime is preserved in subtle correlations within the Hawking radiation, as many physicists now believe, or whether it vanishes entirely, violating quantum mechanical principles, remains one of the deepest questions in theoretical physics. The black hole information paradox, first articulated in the 1970s, finds its ultimate testing ground in this final evaporation. The last photon escapes. The last particle pair separates at the event horizon, one member falling inward to carry away the final increment of mass, while its partner propagates outward into the cosmos. The space-time curvature that defined the black hole's existence smooths out. The gravitational well that once trapped light itself, flattening into the uniform geometry of empty space. Where once there existed a region from which nothing could escape, there now exists only the fading thermal glow of the evaporation's aftermath, photons spreading ever outward through the expanding void. The universe has lost its last gravitationally bound structure. No stars remain, their nuclear fires having exhausted themselves across timescales of 10 to the 14th years. No white dwarfs persist, their crystalline cores having dissolved through proton decay over 10 to the 40 years. No neutron stars endure, their degenerate matter having succumbed to the same quantum instability. And now, no black holes survive, their event horizons having evaporated through the patient action of quantum field theory in curved space-time. The energy that once constituted this final black hole now exists as radiation spreading through space at the speed of light. This radiation carries entropy, the thermodynamic measure of disorder, in its statistical distribution of photon energies and directions. The second law of thermodynamics, that entropy must increase in any isolated system, has guided the universe from its low entropy initial state through the ordered structures of stars and galaxies to this final condition of maximum disorder. The gravitational clumping that created cosmic structure, the nuclear fusion that powered stellar evolution, the accretion that fed black hole growth, all of these processes generated entropy that now disperses irreversibly through the infinite void. The cosmic clock, measured in units of 10 to the 100th power years, has completed its count of the black hole era. The universe that remains contains only the most stable forms of matter and energy, particles and radiation drifting through space that continues to expand according to the equations of general relativity. The temperature of this radiation, once the 2.7 Kelvin glow of the cosmic microwave background, has redshifted to values indistinguishable from absolute zero. The density of matter, once sufficient to form galaxies and stars, has diluted to levels where individual particles occupy volumes larger than the observable universe of the stelliferous era. This transition marks the boundary between the black hole era and what cosmologists call the dark era, the final epoch of cosmic history. The universe has not ended in any dramatic sense. Space continues to exist, time continues to flow, and the fundamental laws of physics remain unchanged. But the capacity for change, for the creation of ordered structures, for the concentration of energy into useful forms, has been exhausted. The cosmos has reached a state of thermodynamic equilibrium from which no further evolution is possible, a condition of maximum entropy that will persist, according to current understanding, for eternity. The dark era unfolds across temporal expanses that transcend human numerical intuition, stretching beyond 1 × 10 to the 100 years into a future where the very concept of measurement loses practical meaning. In this final epoch, the universe has achieved a state that physicists describe as heat death, not the absence of heat in the colloquial sense, but rather the complete equilibration of temperature across all of space. Every region of the cosmos has settled to the same infinitesimal temperature, a fraction of a degree above absolute zero, and this uniformity eliminates the temperature gradients that once drove all physical processes, from stellar fusion to planetary weather to the metabolism of living organisms. The particles that remain in this equilibrated cosmos consist primarily of photons, neutrinos, electrons, and positrons, the stable products of all previous decay processes. These particles drift through space at densities so low that meaningful interactions become vanishingly rare. The average distance between any two particles exceeds the diameter of what was once the observable universe, and the expansion of space continues to increase these separations exponentially. A single electron might travel for 10 to the 120 years before encountering another particle. And when such encounters do occur, the energies involved are so minimal that nothing of consequence results. The photons that permeate this cosmos represent the final repository of the universe's radiant history. These include the red-shifted remnants of the cosmic microwave background, now stretched to wavelengths measured in light years, carrying energies of approximately 10 to the -30 electron volts. Mixed among them are the photons produced by Hawking radiation during the evaporation of black holes, similarly redshifted to wavelengths that span astronomical distances. The temperature of this photon bath has fallen to approximately 10 to the -30 Kelvin, a value so close to absolute zero that the distinction becomes philosophically rather than physically meaningful. Neutrinos, those ghostly particles that once streamed through stellar cores and supernovae, continue their eternal journeys through this emptied space. The cosmic neutrino background, a relic of the universe's first second, when temperatures exceeded 10 billion Kelvin, has cooled to temperatures even lower than the photon background, approximately 1.95 Kelvin in the present era, but now reduced to values below 10 to the -30 Kelvin. These neutrinos possess such minimal energies that their interactions with other matter, already extraordinarily rare, have become effectively impossible. They represent frozen information from the universe's earliest moments, traveling forever without destination or purpose. The electrons and positrons that survive in this era exist in a curious quantum state. At such low temperatures and densities, these particles no longer behave as discrete objects in the classical sense. Their quantum wave functions spread across volumes of space that dwarf galaxies, and the uncertainty in their positions encompasses distances that would have taken light billions of years to traverse in the stelliferous era. When an electron and positron do eventually encounter each other across these vast probability distributions, they annihilate into photons with energies so low that the resulting radiation is indistinguishable from the background thermal bath. The geometry of space-time itself has evolved during this dark era. If the universe possesses positive cosmological constant, as current observations suggest, space continues its accelerating expansion indefinitely. This expansion further dilutes the already sparse particle population and stretches photon wavelengths toward infinity. The observable universe of any hypothetical observer shrinks as the cosmic horizon contracts, eventually encompassing a region containing, on average, less than one particle. Each particle becomes isolated within its own observable universe, causally disconnected from all others. The thermodynamic state of this cosmos represents maximum entropy, the condition toward which all isolated systems inevitably evolve according to the second law of thermodynamics. Entropy, often described as a measure of disorder, more precisely quantifies the number of microscopic arrangements consistent with a system's macroscopic properties. In the Dark Era, the universe has explored essentially all possible configurations and settled into the state with the greatest number of equivalent arrangements. No gradients remain to drive change, no concentrations of energy exist to perform work, no temperature differences persist to power engines of any kind. This equilibrium state possesses a peculiar form of stability. Small fluctuations continue to occur as quantum mechanics permits temporary violations of energy conservation, particles briefly appearing and disappearing in the vacuum. These fluctuations, however, cannot accumulate into larger structures because no mechanism exists to concentrate their effects. A quantum fluctuation that momentarily creates a particle-antiparticle pair finds no gradient to separate the pair before they annihilate, no field to accelerate them in different directions, no structure to capture their energy. The fluctuations occur and dissipate, leaving the average state unchanged. The question of whether this equilibrium persists eternally or eventually gives way to new phenomena remains at the frontier of theoretical physics. Some calculations suggest that quantum tunneling events, given sufficient time, could nucleate new regions of space-time with different vacuum energies, potentially spawning new universes with their own physical constants and evolutionary histories. The timescales for such events, if they occur at all, exceed 10 to the power of 10 to the power of 10 to the power of 56 years, numbers so large that writing them in standard notation would require more digits than there are particles in the observable universe. Whether such processes represent genuine physical possibilities or mathematical artifacts of incomplete theories remains unknown. The concept of time itself becomes problematic in the Dark Era. Time, as measured by physical processes, requires change to have meaning. A clock functions by counting regular oscillations or transitions, but in a universe of perfect equilibrium, no such regular processes occur. The occasional quantum fluctuation provides no reliable periodicity, and the intervals between particle interactions span durations that exceed any meaningful measurement. Whether time continues to flow in any physical sense, or whether the Dark Era represents a kind of frozen eternity, depends on philosophical interpretations of temporal concepts that physics alone cannot resolve. The universe, having begun in a state of extraordinary low entropy, concentrated in the hot, dense conditions of the Big Bang, has completed its thermodynamic journey to maximum entropy. This trajectory, spanning approximately 10 to the power of 100 years from the first moments of cosmic expansion, to the evaporation of the final black hole represents the complete history of structured existence. Stars formed and died, galaxies assembled and dispersed, life perhaps arose and contemplated its cosmic context, and all of it constituted a brief fluctuation in the universe's inexorable approach to equilibrium. The Dark Era continues, silent and unchanging, a cosmos that has exhausted its capacity for novelty, yet persists in its fundamental existence. Space remains, time perhaps flows, and the laws of physics hold their eternal validity over a domain where nothing remains to obey them in any interesting way. This is not an ending in the narrative sense, but rather a completion. The universe having fulfilled its thermodynamic destiny and settled into a state of perfect, eternal rest.